So welcome everyone to the 6th day of the summer school. Today I have the pleasure of introducing Chris Dyer. He's a scientist at Google DeepMind, and I believe he's still a professor at Carnegie Mellon University. At least he was for a long time. Many people probably know him because of the vast and interesting research he published over the years in machine learning and NLP. And he's also a speaker in LXMLS for many years now. I believe it's like 9 years, if I'm not wrong. So today he will be talking about modeling structured data with neural networks. I really like these talks, so I hope you like day 2. Okay, you have the floor, Chris.
All right, thank you very much. It's really nice to be back at LXMLS, I believe, yes, for the 9th time. And I hope that next year we'll all be back in Lisbon in person for this. So today we're talking about what neural sequence models can do and how they work, mainly how they work. But I want to start out by talking about what they can do. And I think if you look around and sort of say, why are people excited about deep learning? What you'll find are examples of neural sequence models. And so I'm sort of honored to be able to give this talk, because this is really at the heart of what people are excited about these days. If you go to Google Translate and put in some Portuguese text, a neural sequence model can tell you a pretty good translation into English of a description of the Bairro. And for those of you who haven't yet had a chance to go in person to Lisbon, only here virtually, I really recommend that you go and visit this wonderful neighborhood. Now, at this point, almost 3 years ago, what really kind of got people excited about the creativity, you might say, of these models was the ongoing work from our colleagues at OpenAI with these series of GPT models that are basically, you would give them a little prompt of text and ask them to continue it. And they really can demonstrate that not only do these models kind of understand how language works at the low level, sort of how syntax and grammar and things like that fits together, but they but they understand how to put something that sounds like a press release together. So they really understand kind of global document level structure. Now, of course, these models aren't perfect. There's a casos seculares. I don't exactly know what that means in Portuguese, but we don't have the term secular houses in English. Presumably, this is a standard term. There's a little bit of inconsistency in the kind of language models, so you can always find some examples. If you look closely, you'll see all sorts of problems. Another particularly exciting example of neural sequence models that we saw just come out in the last couple of weeks are these examples of code completion. So just from a description, a little comment describing what a function should do, a function declaration, and a bunch of training on the corpus of all of the publicly available source code on GitHub, you can build a neural sequence model that can predict the behavior of the or what the function, how it should be implemented. And this is really quite remarkable. So today we're going to talk about the architectures that these systems are built on. We're going to start from a very small description of kind of the basic primitives and build up to what's called the transformer architecture, which is used to model all of this stuff today. So all you need then is, you'll have the understanding, all you'll need is to find is a bunch of big computers and some interesting data to train it on, and you'll have the know-how to roughly to build everything that you've seen demoed here at the beginning. So the organization of this morning's lecture is as follows. So we're going to start with recurrent neural networks and talk about an application, the application of language models, and also give a proper definition of language models. And then we'll actually have a little opportunity in there for some quick questions. And then we'll talk about the learning challenges and solutions associated with recurrent neural networks, because they are a good example of, you start with a kind of good idea for how to solve a problem that is defined by kind of what we want the good inputs and outputs to be. We want to model sequences, but the initial guess at sort of how to solve the problem wasn't quite right. And I think neural networks gave a really good example for how you analyze the limitations of a model and build a better one by understanding, by some analysis of what's going on mathematically in these systems. And that'll build up to what was popular a few years ago called long short-term memories, LSTMs, and gated recurrent units. And these still are actually quite important in some applications. And then we'll have a proper break for about half an hour. And then in part two, we're going to talk about conditional language models. So these are things where you've got some language models where we want to generate text in some context. And we want to figure out how to represent that context to the model. These are broadly subsumed with what are called encoder-decoder architectures. So we're going to encode the context, and we're going to decode the representation into the output that we'd like. And then we'll talk about two large classes of such models: sequence-to-sequence models with attention and RNNs, and then transformers and self-attention. And this end section, transformers and self-attention, are roughly exactly what powers all of these kind of current exciting models. So let's dive in. So I'd argue that sequential data is most of the interesting data that we're interested with in nature. So you can think about things like words in a sequence, words in sentences, documents, conversations, turns in a conversation. So if you want to build a dialogue agent that you can think of as a sequence. Nature itself has a lot of sequences. The sequence of our genetic code, the amino acids that form proteins, all of these things we've become very aware over the last couple of years are extremely important, and being able to process them has huge benefits. Stock market returns can be seen as a sequence. Any other sort of time series, economic time series are another examples. But obviously things like tokens in a program, actions taken by an agent while playing a game, even things like the sound amplitudes in an acoustic signal. So you can build a text-to-speech system as a sequence-to-sequence transduction problem. Even the pixels in an image are sequential in nature. So really, if we can solve this problem to a first approximation, we can solve almost every interesting thing you might be able to go out and find in the world. So we're going to distinguish two kinds of sequence modeling tasks. So in the first, we want to condition on sequential data and make a prediction. So for example, we might want to read a review and decide whether it's positive or negative. So imagine you want to run a e-commerce site, and you want to, for your customers, you want to describe whether you want to show them some examples of positive reviews and some examples of negative reviews. You don't want to just show the most recent one. So you build a classifier that wants to read a review and makes a decision. Does this sound like this is something that was positive or negative? So that's an example where we want to condition on a sequence and generate a smaller output. In other applications, we want to generate sequential data. We've started in this summer school talking about some very basic ideas like part of speech tagging. You can view that as a generation problem. So the output of the problem is a sequence of part of speech tags. But of course, now we're seeing very, much more exciting things where we're generating a sequence of code, a summarization of the document, a translation, even producing a weather report or a summary of Sunday night sad football game. These are all outputs of sequences. But in many cases, we also want to do both. So in translation, for instance, which is a problem that I've worked on for many years, we want to read a text in Portuguese, say, and we want to generate its translation in English, or we want to read a long document and provide a short summary that doesn't take as long to read. So in many of these cases, we both want to condition on sequential data, and we also want to generate sequential data. Okay. So we're going to start as a motivating example of how we might build one of these sequence generating models with the case of language models. So formally, a language model is going to assign probabilities to a sequence of words W, where we've got a length L and we have a sequence of tokens W1 through WL in order. And these we're going to assume are drawn from a finite vocabulary. So these will be say, words in English. Well, what if there, how many words in English are there? Actually, there are an unbounded number. We can create more. We're going to still, for simplifying purposes, assume that we can close this vocabulary and only work with a fixed vocabulary. So anything outside of that will effectively have a probability of 0. So it's convenient, but actually not necessary. Anything that follows the rules of probability and assigns probabilities to a sequence of any sequence of words is a language model. But what we're often going to see in deep learning is that we want to decompose this probability using the chain rule for probabilities as follows. Now, you'll have heard of the chain rule for derivatives, which we use to derive back propagation and things like that. This is one of the many chain rules that comes up in mathematics. And that just says that we can write the probability of a joint distribution over, say, all the L words in sequence by taking the probability of the first word, multiplying it by the probability of the second word given the first word, the third word given the first 2 words, and so on. And in fact, you can actually decompose this in any order, but because we speak sort of from start to finish, we also tend to model these things from start to finish. And the important thing here is this holds exactly. You can write any complex probability distribution in this way. And we can simplify this, writing it in terms of this product notation. And the reason I went through this is this chain rule changes the way, by writing it using the chain rule, this changes the nature of the language modeling problem from this, like, how do you model a big joint distribution over a bunch of words, to modeling the probability of the next word, so the teeth word, given the history of the preceding words. So this is a really interesting thing because for conditioning problems, obviously, as we started with the example of read a review and make a decision, we have to represent a sequence. But for this generation problem, we actually just need to solve the same problem. We need to represent a sequence, so some summary of that sequence, and then make a decision about what comes next. So in some sense, basically, we have to answer this question: how do we represent an arbitrarily long sequence in an intelligible way and learn to work with this? And that's the one problem that we have to solve in order to really do a lot of work with sequence models, both for generation and representation purposes. So the way we're going to do this is we're going to train a neural network to build a representation of sequences of unbounded lengths. And so I'm going to talk a little bit about neural networks from the perspective of representation learning, because there is actually an alternative view, and it's still actually a very important view, where often we come to a problem and we know something about the way the world works. We understand the causal mechanisms that underlie reality. And so when we present sort of the independent variables to a model, we want to present the things that we know are going to influence the outcome of the process that we're seeking to model, rather than things that we don't think are or we know not to be correlated. Of course, with language, we have a lot of us spent a long time studying language scientifically. We understand a lot of it, but one of the sort of humbling things about studying deep learning is we realize just how incomplete our knowledge of language is. And so neural nets are a great tool for letting the model figure out the relevant variables. So let's talk about feature induction. So I'm going to go back to something that you'll have covered earlier in this in the summer school, linear regression. So in linear regression, our goal is to learn a parameter matrix W and a vector B such that this loss F is minimized for a data set consisting of M training instances. And classically, linear regression is one of these problems where the X's must be selected or designed carefully. Often these are things that you can go out and measure, or these are things that you can derive experimentally. So these could be, if you're predicting, whether it's going to rain, these could be things like the humidity on the day before, whether it rained the day before, things like that. And you're going to try and predict, say, how much rain will fall the next day. But if you get the wrong things in X, you're going to be in trouble. So another way of thinking about this is to use, rather than a linear regression, where there's going to be there's an assumption of linearity between the inputs X and the outputs Y. We're instead going to assume that X are sort of naive features. These are things that, rather than being necessarily even correlated in any way, are just going to be things that are very easy to measure. In fact, maybe we're just going to measure everything we can, and we're going to learn the transformations, any sorts of transformations, not just linear ones, into this hidden representation H, which we see here. I guess I can't get my pointer over there. So this H then is going to be substituted into this Y hat equals WH plus B on the second line down at the bottom of the slide. And if you'll notice, this is exactly what linear regression looks like. So if we have a good learner for this H, the hope is that given these naive features and this more powerful learner, we're going to be able to learn something that has all of the constraints necessary to be a good linear regressor. So it's going to, be non-collinear. It's going to be, there's going to be a linear relationship between H and Y, all of this good stuff. And so you might say, well, gosh, why don't we do this all the time? And it turns out we should do this often. It's if your goal is to get good predictive performance, then this is a good thing to do. Now, of course, we don't just, in science, we're not just interested in good predictive performance. We also often want to understand things. These models are harder to interpret, but that's all I'm going to say in general about this, unless questions come up. So you might ask, okay, you've just added one little layer where we've got this, where we've transformed these, what I call naive features, by multiplying them by a linear map, adding a bias, and then passing them through this nonlinearity. So this nonlinear function is generally going to do some nonlinear transformation of each element in that resulting vector. Usually it's going to look like a sigmoid function, but there are other sort of more exotic things out there. And you might ask, what functions can this parametric form compute? And one of the remarkable results is that if H is big enough, that is, if there are enough dimensions, it can represent any vector valued function to any degree of precision. So obviously, this is a much more powerful regression model. Now, I do want to caution you here that just because you can represent things, there are two issues here. It doesn't mean that given even a large amount of training data that you're going to succeed at learning this. It can be still very hard to learn this. And second, that it will be practical to represent things. So it doesn't mean that this model is kind of all you need, but it does get you a long way there. And it does show that actually sometimes these very subtle tweaks to the form of a model change the power immensely. So if you get rid of that nonlinearity, G, and replace it just with the identity function, well, it's very easy to show that this you haven't actually added any power at all to the model. You're still just taking, in that case, an affine transformation of X and predicting Y from that, which is far less powerful. So, but the point I wanted to make here, largely in the context of this lecture, is you can think of H as the induced features in a linear classifier. So rather than having to say, what are the things that stand in a linear relationship to the things that I want to predict, the Y's, which is a hard task, that first part of the model did the job of a feature engineer. And as I said about the sort of humility in working in deep learning, especially if you come from a background where we sort of try to figure out what some of these features were, these networks are really good at it. And I've completely given up on the idea that I could ever engineer features nearly as well as a neural network. So this is a very powerful tool indeed. So let's move on to recurrent networks. So here's a little bit of a graphical notation representing the thing that we just saw. This we can call a feed-forward neural network. So we're going to move from a vector X, and we are going to see this arrow as roughly do a linear projection or an affine transformation of X, possibly followed by a nonlinearity. So we can sort of diagrammatically represent this. And a recurrent neural network is going to introduce a loop here. And so what we're going to see here is that at every, first of all, we're going to have these things indexed by time. So we're going to assume that rather than having a single X as an input, we're going to have a sequence of X's. These will each be vectors. And likewise, we're going to have a sequence of these HTs, these induced representations of the XT. But we're also going to make the assumption that we want HT to depend on what happened before in the sequence. So we want to remember certain things about the past in order to build a better representation. And then at HT, we're going to make a prediction about YT. And so what we're going to do is we're going to use this form where, in addition to taking a linear transformation of the current input, we're going to take a linear transformation of the representation that was computed at the previous time step, and then everything else remains the same. Oops. So one thing to notice here is we've actually got just one linear transformation. So if we think about concatenating the input to the network at time t, xt, with the representation of the network at the previous time, you can sort of see that we're actually just using a sequence of feed-forward networks that have a pair of inputs, one being the kind of previous hidden state and current input. And then we're going to build a representation this way. So this kind of puts recurrent neural networks on sort of familiar footing, I think. And so here I'm going to show that there's this, graphically that there's this loop here. Okay, so how do we work with these things? So obviously, we can't we can't do computations where there's a loop. So we're going to assume that we have, at time 1, we're going to have an input x1, and we're going to compute h1, but we're going to need some sort of representation h0. And that we can actually just set as a learnable parameter, or we can say, well, just use the 0 vector. That's often widely done. And then we're going to unroll this given the sequence that we've got. So say we have 4 inputs paired with 4 outputs, and we are going to generate h1, 2, 3, and 4 from this, and then make predictions y hat 1, 2, 3, and 4. So the big question now is how do we train the RNN's parameters? So you'll have seen how this works in regular feed-forward neural networks. We now have a computation graph that we can apply backpropagation to, as long as we have some targets. So if we have a target y1, we can compare the prediction of the model y hat 1 with the given target y1 and compute some differentiable cost function. Now, this does need to be differentiable. That's one of the restrictions. Obviously, there are many things that we would like to be able to compute that are not differentiable. You can hear about some of the techniques for this later when you get to reinforcement learning. But we're going to today assume that all of the cost functions are going to be differentiable. This could be something like the Euclidean distance between the 2 vectors, or the cosine distance, or we'll talk about some other ones that are sort of specific for working with symbolic data in a moment. And we're going to assume we have one of these at each time step, right? And so now we've got 4 costs. So this is a little bit different than what we had when we were working with feed-forward networks, because we just kind of had one target that we were backpropagating from. And so what we're going to do is we're just going to sum across all of these positions to get a single loss. And then this is going to be the thing that we then backpropagate from. So once we unroll this graph, that loop that we had in the representation of the recurrent neural network goes away. We have a well-formed directed acyclic computation graph. We can run backpropagation on this. And crucially, all of the parameters that we use, these V's and W's from the matrices, and B and C, the bias vectors, those are going to be tied across time. So we're going to use the same one over and over again. And historically, if you read old papers, you'll see this referred to as backpropagation through time. We're now, thanks to sort of the fact that we outsource our kind of backpropagation thinking to automatic toolkits. We don't usually worry about this. We just assume this can be built. But I think to really understand what's going on under the hood, it's worth thinking about this. So basically what we're going to do is we have these 4 inputs from each of these losses. They're going to aggregate together, and we're going to differentiate this F with respect to each of these things and run the backpropagation algorithm. So let's consider what happens here with, say, this U parameter. So this U matrix is the thing that influences how the previous hidden state influences the subsequent hidden state in the recurrent network. So we call these H's, we'll refer to them as the hidden states. And you might augment this graph a little bit by showing the dependence of each of these H1, H2, H3, and H4 on that parameter U. So that value is implicitly feeding into it. So when we start our backpropagation and run, we're eventually going to end up computing a derivative of each of those H1s with respect to that U. And since we have effectively little bits of derivative coming in from each of those positions. We're just going to sum all of those together. And that's going to be the derivative of f with respect to u. So you can see this written out here as follows. So parameter tying also came up when learning about the transition matrix for HMMs. In fact, in the sort of early history of neural networks, the person who named the hidden layers of neural networks had gone off to IBM in the 1980s, where they were working with hidden Markov models to study speech recognition, and they had kind of pioneered this, and because they were called hidden states, this was Geoffrey Hinton, he went and said, I'm going to call these the hidden states of a neural network. And so there actually is a very, at least historically, deep connection there. So why do we want to tie these parameters? I mean, isn't we read, all of you, if you go out and read the, popular kind of AI press, you'll hear like, oh, OpenAI built a model with 180 billion parameters, and we're gonna get to, and then Microsoft is like, no, we're gonna get to 1 trillion, and there's this kind of race. So do we really want to tie parameters? I mean, couldn't we get more if we kind of untied them? Well, parameters are costly on one hand, so we don't always want to have to learn them. Although potentially, if you have a lot of data, you can learn them. But more importantly, I'd say is, in the limit, we do want to be able to deal with arbitrarily long sequences. There's a lot you can do if you just kind of fixate on a very small fixed size input. But if you really want to sort of be able to deal with anything, at some point you have to start reusing stuff. You have to have a model that has some sort of recursion. You can't just have new parameters at every time step. But if you always have short sequences, and I will actually say that this is to a certain extent the direction that we're going these days, that we make sequences kind of not short, but short enough, and then inside the sequence length of, say, up to 1,000, we kind of just model things with independent parameters. Assuming we've got enough data, you can do really, really well. But if you do untie parameters in this way, you just don't have an RNN anymore. So this is the class of models that we're working with for now. Okay, so what else can we do? So this training procedure that we just talked about is great if you've got a pair of inputs and outputs. So this could be something like, X could be a representation of meteorological measurements, and Y could be, say, forecasting tomorrow's temperature or something like that. So we have measurements at every day, we have predictions at every day, but we don't always have that. And RNNs are still great for other things. So another really important task is read and summarize. And based on sort of how we started this discussion about the importance of summarizing a sequence, you might see where we're headed with this. So we want to summarize a sequence into a single vector. So what we're going to assume here is that we have sequences, say x1 through x4, and then we have only a single target. And we're going to assume that that is associated kind of with the entire sequence. So in this case, we're not going to bother making these predictions of these y hats on h1 through h3. We're just going to wait to the end and only compute that y hat once we've concluded the sequence. And at this point, actually, you can think about representing kind of what does it mean to represent a whole sequence in a couple of different ways. So you don't necessarily have to just take the representation of H4 and say that represents the whole sequence. One thing that will tend to do is give a bias towards representing kind of what happened later in the sequence, it'll be easier for the model to learn to depend on it. And so this is an instance of what we call an inductive bias. So if there are two explanations that the learner could, two patterns in the data that the learner could pick up, where you could explain a prediction on the basis of something that happened early in the sequence or late in the sequence. If you used this model, you would probably expect that the learner would discover that the later explanation holds more value. But if you didn't think that that was necessarily the case, if you brought sort of prior knowledge to this, you might want to shift the inductive bias. So this architecture could say something like, why don't we take a function of all of the hidden states across time, a differentiable function. So here we're going to take the element-wise max function, and we're going to compute some sort of consensus hidden representation, h bar. It could be also an average. It could be, you know, anything differentiable here. And that's going to be the thing that we use to predict our sequence output. And again, this is going to shift the thing. So here, because this max function isn't biased to have any particular preference for beginning or end, we might hope that in this case, it would be easier to learn dependencies on things that are occurring earlier in the sequence. And the decision about what to make is really quite problem specific here. So in some cases, having a bias towards representing things later on in the sequence is actually good. So we don't generally do things like this, for instance, in language modeling, where we want to take the end of the sequence and predict what comes next, because we actually do think that when we predict the next word, sort of being biased to pay close attention to what has just recently happened, is actually a very good bias. But that really isn't always the case, and it really does require a little bit of insight into problems. So this is how, when you're deciding what model to use on various things, this is how you should be analyzing things. I want to take a step back a little bit and also talk about recurrent neural networks as an example of a general strategy for representing data that is structured and complex. So the title of this lecture is actually representing structured data, and you know, sequences, as I argued, you know, really get you a long way there. But there's a whole lot of other interesting stuff out there: graphs, trees, everything else like that. And one way that we can think about where recurrent neural networks came from is in terms of a recursive definition of what a list is. So for those of you who started your programming lives in a maybe functional programming language, you'll be familiar with this sort of definition of a list, where you say, well, the empty list is a list. And then we have an inductive step that lets us take what we already have is a list and extend it a little bit. So if we say that T is a list and H is an atom, then T concatenated with H is also a list. And these two things allow you to represent any list because, you know, of any kinds of atoms. And if you think about the definition of RNNs, this is what RNNs do. They compute representations recursively according to exactly this definition of a list. So they define or learn a representation of the base case. That's that H naught we started with. It could be the zero vector, it could be learned. And then they learn a representation of the inductive step. So they're going to assume that there's a hidden representation given of that existing list. That's the HT minus one. And they're going to have a representation of the current atom. Those are the XTs. And then we have this decision about, given those two inputs, what is the representation of the composed thing? And this allows us to generalize, and we know that we're always going to be able to, even given one more atom up until, you know, the end of time, we're going to be able to build a representation of that. So anywhere you can come up with a recursive definition of a data structure, you can neuralize it, so to say. So, trees can be defined this way, graphs can be defined this way. Go out and study your data structures in functional programming languages, and you'll find many things that you can imbue with neural networks. So this is another way of kind of maybe thinking a little bit about what's going on inside of these recurrent neural networks. Okay, so I'm now going to compare these a little bit to some of the other kinds of modeling assumptions that we make in the world. So in an earlier lecture, a common strategy in sequence modeling is to make a Markov assumption. So that also starts with the chain rule, as we've been using this morning. But Markov instructs us to forget the distant past. So again, this gets to that inductive bias question. So if we have to forget something, should we preferentially forget the past or the distant past or the recent past? And of course, is this valid? No, it doesn't hold anymore with equality, but it's practical. It reduces the complexity of the modeling problem. It simplifies the number of parameters if you're representing all of these things explicitly. So this is why RNNs are great for language, though. Although they may have a certain bias towards representing the recent past, they actually, inside of each of those HTs, they can remember anything as long as the learner has decided this is important. So there are no more explicit assumptions. And in comparison with a Markov model where there's no matter how important something that happened at the beginning of the sentence is for making a decision later, you can always potentially recover it. And I'll give you a second to think. What are some examples of things if in, say, my favorite sequence modeling problem, natural language sentences, where I can make a better decision about something that happens at the end of the sentence if I know something that happened at the very beginning of the sentence. We can maybe discuss this in the break. Okay, so now let's actually write down what these history-based language models with RNNs look like. So we've got our sequence. Now, instead of these sort of anonymous X1, 2, 3, and 4, we're going to have these words. So these are going to be words from a fixed finite discrete vocabulary. We like the word cat, dog, something like that at each time. So I am going to draw a colored in circle here with the name of the variable inside. This is a observed random variable. Given that random variable, we're going to compute some embedding. So for every token, every word type in the language, we're going to associate a vector embedding with it. And we're going to, these are just going to be free parameters that we're going to look up. And we're going to be able to say this vector is the representation of the word cat, say. And then we're going to compute at each time step a hidden state and progress things through the network. And so after we've read, say, 4 W1, 2, 3, and 4 words, we're going to compute the representation H4. And now we need to generate a word. So this is a little bit different. We've been talking about vectors so far. So how do we get a vector how do we take a vector and predict a word? Well, what we're going to do is project using a affine transformation. So that's multiply H4 by a matrix. And the input dimension will be whatever dimensions we have chosen for the size of our hidden dimensions for the model. And the output size is going to be the size of the vocabulary, which, as I've said, is going to be finite. And so we're going to have a score. Then you can think about each element in the resulting vector as being associated with, as being a score that says how happy the model is that that word would happen next. And then we're going to pass this through a special function called Softmax, which is going to transform these scores, which will be anything from any real number in every position, to a probability distribution. So a probability distribution over a finite set. Each of the elements has to have a probability between 0 and 1, and if we sum up all of the elements that can, all of the events that can happen there, they have to sum exactly to 1. So Softmax has that property. So let's drill down on this. I think Softmax is quite an interesting function. So the way we can think about this projection is we're going to get a vector whose elements correspond, as I said, to all of the words in the language. I will say very briefly here, since English and any language can always create new words, there's these softmaxes can get very big. These days, what we do is we tend to generate, rather than full words, we generate pieces of words. These can be very small pieces like single characters, or they can be little groups of frequently co-occurring characters. And if you carefully construct the inventory of these co-occurring characters, you end up with things that can generate any string of characters in the language, but you need fewer pieces to generate what you might call likely sentences. And these are sometimes called word pieces, and these are completely common these days. But for today, we're just going to assume that these things are vocabulary items. So the form of softmax is, of course, we're going to exponentiate each of the scores that comes out of this affine transformation, so one for each word, and then we're going to divide them by the sum of the exponentials. And I know, most of you will probably have, you download Torch and get started, and on the first day you use a softmax function, and we think of these things as just sort of given. But there was a time, really only about 30 years ago, when this was new, and there's actually a paper where people proposed this, and it's actually a sort of interesting paper to go back and read. This function turns out can be implemented very nicely in silicon and things like that. So it was actually new at once at some point. Okay, so basically, now in our RNN model, what we're going to do is we're going to be modeling a sequence of words E, so E for English words, say, starting with E1, then we're going to model E2, 3, and 4, and so on. And we're going to, at every time step, we're going to be including in our hidden vector H, which you might think of as the history of the word, of those at each time. So the way this looks schematically, the way we might use this to generate from this, there's actually you can always view a probabilistic model as being associated with a sequence of events. So we're going to start with a special sequence starting symbol. We're going to feed this into our neural network. We're going to get an embedding of that special starting symbol, just like we always do, and use this to compute an embedding H1, which will summarize the fact that we're at the start of the sequence. We will project this out and follow it with a softmax, and that's going to give us a probability distribution over all of the words. Now, if we want to generate from this, we can do things. We've got a probability distribution. What can we do with it? Well, we can sample from it. So I've drawn this little squiggle here to indicate that we're sampling from this, and say we generate the word Tom. Now, the assumption in the RNN is that we take that word that we've just sampled and we feed it back in at the next step. And then we're going to re-embed it and compute a new representation. And this is going to represent, okay, what is the sequence history represented with if it is the start of sentence S followed by the word Tom. And now we have a distribution over all of the things that can happen at that point. And we can repeat this process, and we keep repeating this. Our assumption is until we get to a special stopping symbol, which I've denoted /s here. And at each of these time steps, we have computed a probability, which is just going to be a single element out of that softmax. And this is going to give us the probability of that full sequence. And because of this, at each point, we are feeding in the most recently generated things that we're appending in that inductive definition of a sequence and the inductive definition of a recurrent neural network, the most recent atom. We are constantly updating our current representation of the past. So we aren't making necessarily any decisions about forgetting anything. We're assuming that this model remembers everything. So this decomposition is justified in terms of the chain rule. So how do we train these things? So this is nice if we have a trained model and want to generate some new sentences from it. But what if we want to first train it? Well, in this case, we're going to assume that every time step, rather than sampling from the model, we've sampled from the universe. So here we are going to say observe the sentence "Tom likes beer" in some excellent corpus of English that we have built ourselves, we downloaded from the internet. And at every time step, we need to be able to compare a probability distribution with this discrete token to compute a differentiable cost. Now, in previous discussions, we've talked about differentiating something that's sort of obviously differentiable, like the Euclidean distance between two vectors. Here, we're only going to be able to differentiate the cost with respect to these probabilities at a particular point. So there are several things you can use. One is you take the log probability of the element selected. So somewhere in that P1 is going to be the word Tom, and you're going to take that element and say, okay, here's a probability, say it's currently 0.01. The model would be happiest if Tom went up in probability, so we're going to differentiate that log probability. The gradient is going to point opposite, that's going to point in the minimizing direction. We want to maximize it, so we're going to take the negative log probability, and that's going to be the quantity. And this is also called the cross entropy. There are actually other objectives you can use, but it is the optimal objective to use in terms of minimizing surprisal is to use this log loss or cross entropy objective. And just like we did when training RNNs in the first case, we have a prediction at every time step, and we're gonna aggregate these things together, and we're going to differentiate with respect to all of the cost functions and back into the model parameters. And that's the recipe for training. So I want to point out one thing here that I think people sometimes find a little bit surprising, and that is that when we differentiate so at every time step, we propagate the word forward to the next time step rather than something, say, like the probability distribution. And this is actually a slightly subtle point, because we want the RNN to remember not, so if we were to, for instance, propagate, say, some summary of that probability distribution at every time point, the probability distribution seems to have more information, but it tells what the model potentially could do. Whereas if we propagate what we've sampled or what the universe has sampled for us, what we're propagating forward is what actually happened, not what could have happened. So remember, we want our model to represent a summary of what has happened in any context, not just a lot of information. This is a somewhat subtle and important point, and it's a little bit easier for me to talk to you and see your faces and respond to questions, and I apologize for the limitations of this format, but if you have questions, we'll have a break here in just a second. Okay, so if you use this cross entropy objective, you'll be seeking the maximum likelihood estimate parameters. So effectively what you're saying is find the parameters that make the training data most likely. And by doing this, you will overfit. So if you train this long enough, if you keep taking steps, you're going to at some point get very, very close to assigning maximum probability to the sequences in the training data. What is the maximum probability? Well, it's going to be 1 over the size of the training data, total probability for each of the sequences in the training data, and 0 to everything else. Now, you're not actually in practice going to get there. The model precision won't let you. You don't have enough degrees of freedom probably in an RNN, except for very, very small cases to get that. But you do surprisingly get there. So you're going to want to track the loss on a validation set and make sure that you stop early. There are other things you can do like weight decay. And then there's also a very useful technique called dropout, where you add a certain kind of randomness to the computed elements in the network during training, and these will make the model actually. It will make it somewhat harder for it to succeed at minimizing the training error. But the goal isn't really to memorize the training data. In fact, it's not at all. The goal is to do very well on predicting other data that you believe comes from the same distributions. If you're building a model of English and you train on all of the English up until 2020, you hope that all of that model will be very good at predicting the kind of English that you see in 2021. So in contrast to the count-based models that you will have seen in some of the earlier lectures in the summer school, RNNs don't have any problems with zeros. So the only way you can generate a zero prediction, a zero probability prediction in a softmax, well, recall the definition, it's you exponentiate a score as the numerator in that fraction. So that numerator has to go to 0. So what's the logarithm of 0? Well, it's infinity. So you would have to have infinite minus infinity basically coming out of that matrix multiplication. So somewhere in that parameter, you would have to have an infinity. And gradient descent, yes, it can keep adding things to your weights, but no matter how many things you add, you're not going to end up getting to infinity unless you have some sort of floating point overflow, which you'll probably have bigger problems than that. So you're not going to end up with zeros. So these models do tend to assign non-zero probabilities to kind of anything in their support sets. Okay, so just to kind of summarize where we are with RNN language models. So unlike Markov, these n-gram language models, RNNs never forget. So just in a second, we'll see that just because they never forget, they might still have trouble learning to use their memories. So one of the ways of thinking about what an RNN is doing is they are learning to remember things that happened in the past. It's a bit of a strange way of thinking about memory. And we'll see that, in fact, they have trouble often learning to remember the right things. But, you know, we're not just interested in training these things, we're interested in doing things with these models. And, you know, with a model, you have to still run inference algorithms on it. And so, you know, we've covered sort of intuitively two algorithms, one for sampling a sequence from the probability distribution defined by the RNN. We've talked about training the RNN to minimize the cross entropy, something like the MLE optimization objective. And I want you to think for a moment while in the back of your head about how you might find the most probable sequence under the RNet. And that's going to turn out to be both something that we think we'd like to compute, but probably also a very, very difficult thing. Let me pause here and find out if there are any questions that I should be answering.
We have several questions in the Q&A. Do you want them to read yourself, or should I read them to you?
I've found them. I can go through these. All right. Let's see. Going in order. Good morning, everyone. Yes, there will be slides available well after the presentation. I'm sorry, I didn't know I should have sent this in advance. Okay, why is the nonlinearity important in a neural network? Well, so I sort of alluded to this if we replaced the nonlinearity with an identity function. So the product of two linear transformations is itself a linear transformation. So if you have no nonlinearities, you end up just having the outputs that are capable of being predicted by the model have to be linear in the input. And because not all functions are linear, so even something as simple as taking the conjunction of two inputs and making a decision about a third on the basis of that conjunction requires a nonlinearity is hard. Another famous case is the XOR problem, where exclusive OR is this function where it returns 1 if either input is 0 or 1, but not both. So if both are 0 and both are 1, the output is 0. So this is also sometimes called the parity problem. And in fact, when neural networks and this learning algorithm were, or various kind of learning algorithms were originally proposed, there were no nonlinearities, and people were very excited about the possibility of learning from data and experience as a kind of general purpose solution for kind of everything we might want to do. But then in the 60s, this simple function, it seems, XOR, it was shown that you could not learn this without any nonlinearities. And this simple kind of problem was the first strike against neural networks, and people kind of abandoned them as a result of this criticism. But it turns out that just by putting a nonlinearity in, you can represent anything. And one of the remarkable results is it doesn't really matter what nonlinearity you use. There are there are some universal approximation theorems that show as long as you have some nonlinearity in there, given enough capacity, you can represent anything. So basically, what the nonlinearity gives you, just some simple nonlinearity, is enough to bootstrap any kind of nonlinear behavior in a model. And so I guess the kind of high-level answer is, not all functions are linear. But the great thing about these networks is by having many repeated units, even with very simple nonlinearities, you can piece together much more complicated, arbitrarily complicated nonlinear relationships. And because the universe has those relationships, we want our models to as well.
Okay.
Yeah.
You have a lot more questions in the Q&A, which is an option that you have.
Sorry. I say these were in the chat. Let me finish the ones in the chat. Okay, so is the max function related to statistics? Max just says take the maximum. So if you have 4 vectors and you want to take the maximum of those vectors, well, we don't know what the max of the vector is, but we know how to take the max of a set of numbers. So we line up all of the elements, all of the first elements of the vector vector. We take that max, that becomes the max of the first element, second one, and so forth. Okay, separable verbs in continental West Germanic languages, a good example of why long distance dependency, very good example, wonderful example, actually. The simpler answer, I think, is if you start a sentence with a WH word with a question like what, and you need to predict the final punctuation of a sentence, that is an excellent thing to do. Okay. In the Q&A, so what's your view on fixed size representation learning, compressing arbitrarily long sequences in fixed size vector? I'm thinking of the transformer. Yes, this is going to be covered in quite a bit of depth in the second half of the lecture. So let's defer to that. If you're unhappy with the with my answers there, we can discuss in a later question session. Okay, Rakesh asks, is XI transferred through all the hidden neurons, and what will the shape of XI be? Good question. So XI, the shape is, first of all, up to you. So depending on what you're representing, you get to pick how large you would like that vector to be. You can end up, if you are embedding, say, if you have a vector for a bunch of symbols, if you have many symbols, having a very large dimension, you can have a lot of parameters there. It can be something of a challenge. And because of the linear projection from xi to hi, or to that, what's inside the nonlinearity, that's a dense matrix in general. So there is a projection where you're connecting potentially every element in the x vector to every element in H. And because then H is then HT minus 1 is connected to HT, and so forth, yes, these things do continue on. The only thing that doesn't happen is there's no information flow backwards. So the representation of H1 doesn't depend on X4 in these kinds of models. What's the iteration between sending only the hidden expert time step at t minus 1 to step t? Can we also send the outputs of t minus 1 to the hidden state? Yes, this is kind of the question that I was trying to answer at the end, saying, why do we sample and then use H and HT minus 1? So why don't we say sample, or why don't we pass P the full probability distribution? There actually are variants of neural networks that do use the full projected value. Sort of where you put that recursive connection is kind of was a matter of some controversy in the early days of RNNs. In general, because the normative goal of HT is to represent everything that the model needs to know about the past and to make predictions, the goal is just to, we connect it this way because we want it to have that behavior. If we connect up to the probability distribution, we then kind of overload the goal of the probability distribution, which is to predict what's going to happen next, make a very good decision at that time step, but also propagate information forward from the past. So from my perspective, it doesn't seem as appealingly good. Rakesh asks, I'm a little bit confused with the number of neurons and time step t. Let's say we have n neurons in a layer of RNNs. Maybe.
Let me just say, I think this was the first part of the question of the XIs with the shape of XI.
Okay, got it. All right, can you clarify when the outputs, when the LM outputs are word pieces instead of real words, how do we go from these word pieces to real words? Which we want to have at the end of the day? Very good question. So the word pieces are just concatenated together. And crucially, these word pieces will have a space in them. So we actually treat the space as as just another element of the things that we're predicting. Usually there are some constraints on how spaces are handled when we infer word pieces. We don't just kind of put spaces willy-nilly inside of word pieces. We usually say they'll always be on the left or always going to be on the right. But that means that when we concatenate these pieces together, because they have spaces in them, then we just read out the words very straightforwardly. Yeah, it's actually a very easy thing to use. The remarkable thing is that the word pieces often don't correspond to anything sort of obviously meaningful. They might be syllables, or they might look like little pieces of words that would be sort of meaningful to people, but often they're very opaque. It's kind of remarkable that these networks can figure out how to put them together. Okay, instead of predicting softmax on all of the words, can we somehow generate clusters of words? So for example, part of speeches, and predict one cluster by predicting the next part of speech. So yes, you can factorize the prediction of a word into, well, sort of arbitrarily complicated processes. It used to be much more common before we had lots of data and lots of computational power to do exactly, well, almost exactly this. We would predict a word class, and then conditional on the word class, we would predict a word from that class. And that was very fast. We usually didn't use part of speech tags for this sort of thing because a single word can be in multiple parts of speech. Usually we used word clusters that were basically where each word belonged to exactly one word cluster, because then it simplifies training. But yes, if you're interested in predicting parts of speech, you absolutely can do it in this way. Okay, why has the softmax using exponential function become more popular than other functions, for example, LU? The softmax function has so I wouldn't say LU is a common alternative. There are things like the spherical softmax, which basically replace, say, the exponentiation function with squaring and then normalize it. In general, these haven't worked as well. There are several interesting interpretations of the softmax function. So one is that you can view the probability distribution that you're finding as being closest to the input to the softmax under a certain notion of distance, penalized distance. And one of the organizers of the workshop of this summer school has actually shown that if you look at kind of minimizing this quantity, or solving the softmax as this minimization problem, where you are finding the point that is closest plus a Shannon entropy term, you are, that's what the softmax is. And if you think about what Shannon entropy is, it basically says, I want to maximize the uncertainty of the solution of the softmax. So it's saying, I want to be close to the input vector, but I also want to have maximum entropy. And if you think about what we're doing when we model things, we're basically saying we don't want these models to be overly confident because we might be wrong. We're probably wrong about our modeling efforts. I mean, I think, the last year has taught us you can be very wrong about your modeling efforts. So you want to be maximally humble about your predictions. And That means not assigning too much, not sort of doubling down on kind of the predictions the model is confident. You want to maximize your uncertainty while still sort of believing the model. And Shannon entropy gives you a very good notion of this. I think exactly why Softmax is as good as it is a little bit, it's still a little bit mysterious, but it's been shown time and time again. There are many, many alternatives. Okay. Oh, what does an atom mean in the context of the list? So a list is just this complex data structure that consists of many, many elements. An atom is just the name of an element. It just means not a complex thing. It's what goes into the list. Okay, instead of feeding the next token at iteration, can we feed the probability distribution? Okay, I believe I asked this, or the expected thing. Another way of answering this question about the expectation is, what would the model do? What would it learn if you trained it that way? And the answer is, when you're predicting, say, the word at time step 2, so we started with the sentence, Tom likes beer. And at time step 2, we want to know what does Tom do? You know, what's a verb that goes with Tom? And if we only propagated forward the expectation of what happened in the first sentence, we don't know that Tom happened. We just believe a bunch of things could happen, but we don't want to predict what could happen in time step 2 in all sequences. We want to know what happened in time step 2 in that sequence. So if you propagate, say, an expectation of the word embedding forward from time step 1 to time step 2, and so actually what you're doing is you're training a model that says, okay, what happens in general at in a second position, not what happens at a second position given a particular sequence. And usually we want to know what happens, I think, in the second position given a particular sequence rather than in general. Okay, do we need to compute the probability distribution of a sequence over the corpus before training an RNN because we're a prophet? No. So when we compute the cross entropy and when we train our models, what we do is we randomly sample from our training data usually, or we just go through deterministically. But that means in expectation, we're going to hit every sentence kind of with equal probability. So if we think about that as a sampling procedure, we're effectively building a probability distribution through our algorithm. And at the same time, at every position, you know, we are trying to make the model's predicted probability distribution, which is going to be some nice smooth thing. We're trying to get it as close as possible to a probability distribution where we've put all of our probability on the observed token, say the word Tom, and 0 everywhere else. Now, obviously, that's a really bad modeling decision. But an average, because we're doing this over and over again with many, many different things, we're going to be approximating, we're going to be building a kind of histogram that represents that, but we don't have to explicitly compute it. It's implicitly computed. Okay, when applying max HT, prediction, isn't that too risky? So this question asks whether, if we want to summarize the sequence by maxing over all of the vectors, if that's risky. So I will say, in many tasks, it turns out to be actually better performing. So I would say empirically no. And here's the thing I would think about. So the model is going to be trained. You're still going to be training this model by back propagation. And so if the model needs to downweight things or upweight things that happen later in the sequence, there's going to be pressure via the backpropagation algorithm to learn exactly those things. So yeah, the model will figure things out is the hope. So I think exactly what the biases are is actually a little bit hard to say. I'm not comfortable just saying that there is kind of no positional bias because we still have this left to right ordering in the representation building. But I would say this maxing strategy, especially when you're running a bidirectional recurrent neural network, which we'll talk about a little bit later, it seems like it's a reasonably effective technique for certain classification problems. Okay, are there some RNN pre-trained language models that we can tweak for practice on our data? I'll defer that question to the people running the lab this afternoon. Okay, ULM fit models. I am also now forgetting the ULM fit stuff, so I will look that up and get back to you after the longer break. Okay, do a higher vocabulary size require larger hidden layer sizes? That's a really interesting question. I would say that in general, as you increase the number of parameters, you actually can get better generalization performance if these things are well tuned. Usually we use the largest hidden sizes that we can afford computationally. There's some good reasons for this, and I don't think the issue is quite as simple as just sort of saying vocabulary size implies a certain size. One thing that does happen is if you work with very small units like characters and want to model things like text, which of course are sequences of words, which are sequences of characters. Depth matters a great deal, and it is more important that you just have an adequate number of parameters. But I wouldn't say there is a particular relationship with vocabulary size and hidden layer size. Okay. Thanks for the great questions. Why don't we move on, and I will happily take more of these when we meet next. Let me move this away. Oops. Okay. So now let's talk about some training challenges for recurrent neural networks. Let's consider what happens to gradients as you go back in time here. So we're actually going to run the backpropagation algorithm. So we're going to start with f, which is our output, and we're going to differentiate it with respect to itself, which is just 1. And then we're going to say, well, how should we have changed our prediction of f? Our prediction to minimize f, well, that's just the derivative of f with respect to y, and now with respect to h4, h3, h2, h1. So now if we want to know how we should change h1 to improve f, we just need to multiply all of these matrices together here. So we've got the sequence of Jacobian matrices. So if you notice that if we want to know the derivative of the prediction or of the loss with respect to the first elements, the first hidden representation, which we can then backpropagate into x1, which is, say, something we control, we've got this series of this product, which is going to be from time step 2 to the length of the sequence. And as we said, well, with RNN, the sequence length can be as long as it wants. So we're going to have effectively this product in here of a bunch of matrices, which is going to be the number of terms in that product is going to be a function of the length of the sequence. And what happens when you multiply things? If you have something that you multiply over and over and over again. well, let's look what specifically at H1, the derivative of HT with respect to HT minus 1. Well, so obviously this is a fairly complicated thing, so let's do what we do and introduce some auxiliary variables. So let's call the inner quantity in this nonlinearity ZT. And we can now, of course, using our knowledge of the chain rule, just write this product in terms of these two terms. So first, we're going to differentiate dHt with respect to dZt, and then differentiate dZt with respect to dHt minus 1. So we're going to assume that we have an element-wise nonlinearity. And if you differentiate a element-wise function with respect to its inputs, you have a diagonal matrix. So that just means that the change to the output of one variable isn't going to change any other output. You know, basically the only way you change the output of position 1 in your vector is by changing the input to position 1. It doesn't change anything else. So that's where that diagonal comes from. Okay. Now I'm going to watch the chat window and somebody type in what the answer to this question is on the slide. What is what's the derivative of ZT with respect to HT minus 1? Very good. Aha. This is my first successful Zoom question in a big lecture. Great. Yes. So this is just the chain rule for or this is just the definition of product. So we have this U times H, and then we have all these other terms up there which don't depend on H. And so it's just like regular scalar products, we get U. Okay, so what does then the derivative of H with respect to HT minus 1 look like? Well, it's just the product, so it's this diagonal matrix and U. So what happens if we multiply this over and over and over again? Well, we've got a whole bunch of terms of U, and then we've also got this, this kind of diagonal term as well. So there are three cases here. When you multiply a matrix by itself many, many times, it's just like the three cases when you multiply a scalar by itself many times. So if a scalar, if it's equal to 1 and you multiply it by itself many, many times, no matter how many times you multiply it, it's still going to have a value of 1. And the corresponding rule in matrix land is if the largest eigenvalue is exactly 1, you basically get a well-behaved matrix. So you don't have values in the resulting matrix getting any bigger or any smaller. They're sort of shifting around, but this means this gradient propagation is stable. The gradients aren't going to get too big or too small. But if the largest eigenvalue is less than 1, as you do this multiplication, at every step, the elements of that matrix begin to shrink, 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 shrink down. And we call this exponential decay. And if the gradient, if the eigenvalue is larger than 1, then the gradient explodes. And at every step, the kind of results of that product, the elements of that matrix get bigger and bigger and bigger. And because we use fairly simple updates at every time step, this, if we have these changes in values, we have learning problems. And in general, so if you think about the derivative of something like the logistic sigmoid function, that is between 0 and 1. So we are going to, and the way we initialize U, it tends to be kind of having an eigenvalue probably near 1. We're multiplying it by something that makes it even smaller. So we tend to be in a regime where we face exponential decay. So what does it mean if we have exponential decay? Well, what it means is that by the time we take a loss signal from the end of our sequence prediction problem, by the time that signal gets back to update, say, the representation of the first word in the sequence, that it's just gotten very, very small. And so the update that the way you're going to change, the amount you're going to change X, it'll change it in the right direction, but it's just going to take a minuscule step. And we do have, we have fancier learning algorithms that can use momentum and things like that to kind of make a small step into a bigger one. But this is a real problem, and it's very hard to, especially when sort of later elements are sort of dominating those updates to U, for instance, on towards the end of the sequence. Those are going to be big. They're not going to have suffered this sort of attenuation through exponential decay, and they're just going to dominate the learning. And so, in fact, we do see that learning RNNs is very hard. We do see strong evidence of this vanishing gradient problem. Okay. So yeah, as I said, the spectral radius of U is small and gradients vanish. And this means in practice that long-range dependencies are difficult to learn, although in theory, again, they are learnable. There is a setting of the model that you get all the information you need everywhere. So as I said, the better optimizers are one potential solution. There are some clever normalization things that you can do that can help keep gradient norms stable across time. You can do some clever initialization so that you at least start with things that are very close to having a spectral radius of 1. So there's a way of constructing random matrices that have exactly a largest eigenvalue of 1. But I'd say, what we've really found is that you avoid the problem by building a better model. And that's what we're going to turn to. And so, one way of analyzing, if your model is failing to learn things, you can ask yourself questions like what we just did. Did it succeed at actually learning because of a particular, did it fail to learn because of a particular problem in the way it was written down? Okay, so we're going to talk about two alternative RNNs, long short-term memories, LSTMs, and gated recurrent units. And the intuition here is that instead of multiplying across time, and multiplying is the thing that leads to exponential growth rather than, or exponential decay, we want the error to be constant across time. And so, well, what is a function whose Jacobian has a spectral radius of exactly 1? Well, the easiest one is the identity function. So what would be a way of constructing a change to, so where we differentiate ht with respect to ht minus 1, and the Jacobian is just the identity function? Well, a really easy one is we just add the previous value. And so I'm now going to start calling these kind of hidden representations, I'm going to call them memory cells, and we're just going to add. And now when we differentiate CT with respect to CT minus 1, well, it's really easy to see in that function. So there is no dependence on CT minus 1 through f of x, and the derivative of CT minus 1 with respect to CT, well, that's just I. So this is really convenient. So by the way, in the next few slides, I'm going to write this tan h of WD plus B. This is going to be kind of our standard little neural network component with this nonlinearity as just f of a vector. And now I'm going to say that our hidden state at each time is going to be some other nonlinear function of CT. And here's our prediction. So this is, we can call this some kind of like, constant error neural network. So this is really nice. A problem though with this model, well, there are a couple of problems. So the first is that, well, you can see that there is no nonlinear relationship of what goes into the memory at time at time t with respect to t minus 1. And we've had a lot of questions, and I've tried to make the case for why these nonlinear relationships exist. That's basically saying that the past only has an influence on the future in a linear way, and we just know that is simply not the case. So we may have gotten ourselves a little bit more flexibility in terms of representing or in terms of learning, because backpropagation is going to be stable here, but we have sacrificed our ability to represent things. So that seems like a bad idea. So what if we do something like this, where in addition to this kind of constant propagation, our update to the memory cell is this concatenation, this function of this concatenation of the input and the previous hidden state, the previous H. We might call this almost constant. So here we still have this one path where there's this Jacobian I via the addition, but then there is this path through which there's probably this attenuated gradient where things are breaking down. So this is maybe a slight improvement on things like this. But one of the other problems that we're going to have in this almost constant case is that the values inside this memory cell are just going to keep getting larger and larger and larger. And one of the things that we have problems with in these nonlinearities is they begin to saturate when you have extreme values. So if you're constantly adding values, either +1 or -1, they could just get bigger and bigger, and you'll be very quickly in the saturating region of these sigmoid nonlinearities. So if your models have a lot of saturated units, they don't tend to learn as well. So how can we fix this? Well, let's introduce what are sometimes called gates. So at every time step, we're going to update our gate by masking out a little bit of information from the past. We're going to call this a gating function. So we're going to have a forget gate, which is going to decide how much of the past I want to forget. And a gate is just going to be a vector who has as many elements as the vector that we're masking, and it's going to have all values between 0 and 1. So that sigma there is the logistic sigmoid function, and if it's on and everything flows through, it'll have a value of 1, and it can be closed, and nothing will flow through. So we'll make a decision element-wise about how much to forget, and then we'll also decide how much of the current input to allow to be updated. And that's going to give rise to this function, updated function at the top. So basically we do two things. First, we forget a little bit, and then we input. The final change that I'm going to propose here is that each of these hidden states is kind of doing two things. One is it's building a representation that is going to be provided to, that's giving you access to what's in the memory cell for making predictions and also propagating information forward. So we want to make a decision about what outsiders can access in this memory cell. So we'll call this the output of the memory cell at this time. And this is just going to be another gate. And this output is going to be, once we've put things together like this, we have this LSTM formulation, which is still a very, very widely used architecture. And there are a couple of other things that we can do to simplify things. So one is we can say that at every time step, rather than, for instance, deciding to forget a certain amount and update input a certain amount, we can just sort of say that we want these things to be symmetrical quantities. So if we forget something, we want to update that with whatever is coming in. And this often, if you're going to make a change to the LSTM, this is often a very good one. It's kind of a good bias, and it doesn't usually harm performance. Yeah, at any rate, this can be this can be used often with little cost. So you can try this out. Again, these things tend to be rather problem specific. In some cases, it may not, just because you've decided to forget something about the past, it may not be the case that it's now time to replace all the information you've just forgotten intuitively. So here's another visualization of this by a guy who comes up with, I think, very, very nice visualizations of things. Basically, what it says is that at every time step, we have these XTs coming in, we're spitting out these HTs. And we have these kind of two operations, one where we multiply in the forget gates, we're forgetting some of the past, and then second, where we are adding in some new memories. And so this figure just shows how the HTs and XTs come together to make influences about the things we're forgetting, the way we're updating things, and the things that we are propagating forward. So here's another variant that is designed to require slightly less computation than LSTMs, called gated recurrent units. I'm introducing this because not only are they faster, so it may be useful in a kind of constrained resource situation, but because it uses the same addition trick. So basically, at every time step, our HT is going to be again, this convex combination. So we've got this gate ZT, and we are going to forget a little bit of the past at HT, and we're going to add a new sort of candidate hidden representation H tilde T, which is going to be a combination of the representation of the HT minus 1, the current input, and then these two will be mediated via this gate. So here are the kind of three kinds of dynamics for the recurrent neural networks. We see the RNN up top, we see then the LSTM and GRUs. And the big trick here, which is really a useful one to keep in mind, is that addition propagates gradients far, far more stably than multiplicative, highly nonlinear recurrent dynamics. And to me, one of the interesting and remarkable things here is it's not to say that the addition is the only path by which information flows. There are these off-diagonal terms that are, through these F things here on the right-hand side, and there is a path that information flows backwards in time. But by having this addition path, we can train models effectively on longer sequences. And I'm not going to be talking much about very deep neural networks, deep stacks of convolutional networks, but we will see this addition trick used later on in transformer tricks, where we propagate information rather than across time. We're going to propagate it from a low layer of the network to a high layer of network. And this is exactly what makes learning of very, very deep networks extremely easy to do. So it's a good thing to have in your bag of tricks. Okay, so here we've got some time for questions, and then we can take a slightly longer break to give everyone a chance to recover. Are there any questions about this part of the lecture?
There's only one question in the Q&A, I think.
Large number of parameters lead to better generalization only when trained on huge data sets or even with small data sets. So when you work with large numbers of parameters on small data sets, it can work better. It often does. But you have to be very careful with things like dropout and your regularization parameters. But yes, there is basically parameters give you a kind of smoothness in the learning space that are quite useful to work with. So this is actually quite a difference in sort of the traditional analyses of machine learning models, where we just think about kind of the number of parameters as reflecting the complexity of the model. But this, in general, you can improve performance. I'm still working with fairly small data sets right now, and we see basically improved performance sort of no matter how large we make our models, which is a somewhat unfortunate thing. So, you know, really, it's very important. Parameters are extremely costly. And, you know, the name of the game is to balance kind of the performance that you need to do well with kind of the resources that you can reasonably expect to have available. And in many cases, so scale is always one of these problems that you can making things bigger. Usually it's been in terms of larger amounts of data, but these days it's also in terms of larger amounts of parameter. Scaling always works, but we've been in this regime where there are always things that we can scale for a very, very long time. And so you can always gain epsilon improvement through scale, but it's not necessarily the case that scale is all you need to do better. You know, I've been doing this for a long enough time that I remember in 2007 when Google came out with a paper where they trained language models on 2 trillion words of English. These were, you know, Markov language models, and everybody thought, oh well, the game's over. We just need, we'll never be able to compete with Google. And then a few years later, neural language models became popular. They came out of academia, very you know, labs that were you know, could only dream of the resources that Google has, and the solution we figured out quickly was we had the wrong models, even though scale was still, if you scaled, you did do better. But, you know, I think basically the thing to keep in mind is not to despair of, oh, I wish I could scale it more. It's to say, well, look, how do I improve things given the resources that I've got? Okay. Could you explain what gradient propagation means conceptually at a high level? Yes. Okay. So when I draw this arrow, so when we have our neural networks are functions of an input. These are the things that we provide to make the decision to the model. So these will be things like the prefix in a language model, and then we want to make a prediction, which is the output of the model. And in between there are a whole bunch of computations that happen. And in order to learn, we have to compute the derivative of the classification error, that prediction error, with respect to everything in the model, all the way down, and we do this recursively, all the way down to the inputs of the network. And we do this because it's a recursive process. You can think, so recursion depends on a kind of base case. And the base case in backpropagation is the derivative of the cost with respect to itself. And the derivative of anything with respect to itself is just 1. So when we differentiate the loss with respect to itself, it's 1. And then we differentiate the loss with respect to whatever was immediately next to the loss, and so on. And all of these derivatives, because for the chain rule for derivatives, well, actually, similarly to the chain rule for probabilities, they just multiply together. And when you multiply long sequences of things, the behavior of long sequences of products is just very sensitive. And so when we talk about gradient propagation, we say, how does the value of the gradient as you go through more and more of the network recursively back to the beginning, how does it change in value? Does it explode? Does it stay about the same? Does it get smaller? And you know, this part at the end is saying, well, if we don't want it to get too small, a good way of doing that is by having these additive steps, which tend to not result in this kind of multiplication. You replace some of those multiplications with additions, and that gives you a better behaved kind of gradient propagation. And because that's where your gradient is the learning signal. So that's really the name of the game in designing neural networks that can be that can not only sort of in theory compute the things you want, or that you could design a solution, design a set of parameters that compute the solution you want, but actually have a very good ability to learn this from data. Okay. Sorry, what's the motivation for using GRUs instead of LSTMs? Why would you not use the LSTM? Well, it was designed to use fewer matrix multiplications because, this was, developed in the days when, the sort of big companies, the DeepMinds and Google's weren't doing all of the research, and people were really counting every matrix multiply. So these GRUs are faster than LSTMs. Why did we add the memory cells? Is it like a new hidden layer? Yes, it's like a new hidden layer. It was to, I think you might say that the motivation for the memory cells was to separate the responsibilities for remembering the past from a representation of the current state of things that is useful for making decisions at that point. And in an LSTM, at every point, you have to make a bunch of decisions. You obviously have to make a prediction about what is going to be the output at that time, but you also have to make predictions about how you respond to the input. Do you forget things? Do you remember things? All of this. And those are, and the designers wanted to have this like separation of just sort of this very pure memory. The GRU, you'll notice, still looks a little bit more like an RNN. But the sort of key innovation in both of these things is that there's an addition step between the time steps between both the GRU and the LSTM, but there is no addition across time in RNNs. Okay, so given this addition idea, ResNet is basically LSTM for vision. It is. So ResNet stands for residual net, and a residual is this idea that you start with a value and then you make an update to it. So you basically assume your prediction is your input, and then you model the transformation of it. So you can say, if you transpose an LSTM which runs across time, and imagine it goes from sort of top to bottom through depth, if you're sort of doing these constant updates and adding to the representation, you get something that looks very much like a ResNet. So yes, this idea of addition. Another way of saying this is having residuals at every time step. So we'll see this idea of residuals across depth when we get to transformers later on. Okay, so does propagating all the way back to the input mean also changing the word embeddings, for example? Yes, it does. So that is one of the things that we have to backpropagate into. If we would somehow recompose the input from the input vectors, for example, to try to generate the input word based on the tuned input vector, the representations could possibly be so different that the inputs would work differently than what they were at first. So, I mean, it depends a little bit. So if you're using, say, pre-trained word embeddings, and then you allow them to update while the model is learning, they will drift over time. But because you're making relatively small steps throughout the jointly, you basically are ensuring that the model stays in sync. So you never take a huge step. And in fact, some of the interesting work that's been done over the years in optimization seeks to kind of limit the amount that you can change the model such that the changes that you would make in a prediction due to a particular gradient update are bounded in various ways. Another thing that is often done is if you know something about what you want your word embeddings to say look like, rather than allowing the word embeddings to sort of deviate arbitrarily, you can say, well, yes, we're going to back propagate and we're going to allow them to update, but we're also going to say that if they deviate too far, there's going to be another term in our loss that says keep them kind of close by where they started. So these are all very, very valuable techniques that can be used. But yes, you absolutely do want to learn this stuff. Okay, so thanks for the questions. Let's take a break. When should we return? Do we want the full 30 minutes, or are we fine with just 15 minutes? I'm sort of happy with either.
Yeah, 15 minutes it would be. If it's okay for you, then
it's fine with me. So why don't we return at 11:15 and everybody have a quick break, and then we'll have a little more of a gap in the
after this record number of questions, it should be
okay. Right. A few more questions than I had last year, so that's which is great. Then everybody enjoy your break, and I'll be back shortly.
Okay, see you later. Okay, Chris, ready when you are.
Okay. Welcome back, everyone. I wanted to quickly answer Shagun's question about the ULM fit models. ULM fit is a recurrent neural network variant of a language model, and it does use, it's basically trained in the usual way. The difference is this was the first of these sort of transfer learning sorts of problems where you pre-train a language model on text prediction tasks, and then once you've got the trained model, you fine-tune it to do another task. So this is a this kind of transfer learning setup is a very common thing to do. Often you don't have very much data for the task that you're trying to learn, and so a very good strategy is to pre-train on something, say, like language modeling, and then your language model parameters will capture a lot about sort of how language model works, and then, or how language in general works. And then if you have a language understanding test, you can use the representations, those hidden states, possibly modified a little bit via backpropagation to do some task, specific task. And this often learns more efficiently than trying to learn from scratch on the new task. So it is just a regular RNN, but it takes these two things. Oh, and the representation that's used in UML fit is actually kind of interesting. It is a concatenation of the final state, HT, at the end, and then also an average of all of the intermediate hidden states, and also the max across the dimensions. So it's actually kind of a more complicated representation than what we talked about, but it has sort of a couple of different biases all present in that final layer. So hope that clears things up a bit. Okay. So in the next part of this talk, we're going to move on to look at conditional language models. So a conditional language model, like a regular language model, is going to assign a probability to a sequence of words, W1 through L, but given some conditioning context X. And this conditioning context can be just about anything. It can be anything. And as with unconditional language models, it's going to be useful to use the chain rule to decompose the probability. The only difference here is we've got this extra dependence on X on the right-hand side, and that X is never modeled in contrast to the generative language models that we were working with, where sort of everything that occurs on the left-hand side of the conditioning line, we model at some point. So basically what we do here is we've reduced the problem to modeling the probability of the next word, given the history of the previously generated words and the conditioning context of X. So these are great because you can use these to solve a whole bunch of interesting tasks. So for instance, we might model something like, okay, given X an input, let's generate some text. So we might learn to generate text in the style of different authors. We might label, we might have X, our input, be a topic label, and we might be able to generate an article on that topic. We might condition on a sentence in French and generate an English translation. We might condition on an image and generate a text description of the image. We might condition on a document and generate a summary of that document. And we might say condition on a question and a document and generate its answer. There's many, many different things that we can do here. And crucially, the input doesn't determine what we do. It's a pair that we need here. So to train an unconditional language model, we were in a good situation. We talked about this process where we summarize, where we sample from the universe, and we assume that we've got example text. The training data for conditional language models is a little bit more complicated. We need paired samples. So we need examples of context X, and we also need output sequences Y. And one of the big challenges here is that data availability varies considerably by task, and it's very easy to think of tasks that could be solved with conditional language models, but the data just doesn't exist. But fortunately, there are relatively large amounts of data for translation, summarization, caption generation, speech recognition. These are all instances of conditional language modeling tasks, and tasks where we use the conditional language models that I'm going to be talking about to solve them. The other tasks where less data is available, are often now being solved using things like these pre-trained language models and fine-tuning with a small amount of data. That is out of scope for this lecture, but they often work with similar architectures, as we'll be talking about. I'm just not going to be going into the details because understanding the basics of supervised learning, I think, is sort of the important first step here. So I also want to say briefly something about evaluating conditional language models. So conditional language models get to the heart of what we're trying to do AI for, where we're taking an input and we're trying to predict something useful. So, one thing we can do is these are language models. So we can look at ways of estimating the goodness of fit for a language model. And in particular, we often look at cross entropy or perplexity, which is roughly how happy is the model to explain some held up data from the same, say, task or distribution that we think we are trying to solve here. And this is pretty easy to implement. You can screw things up a little bit, but if you're careful, it's easy. But the values of these things are rather hard to interpret. Like, yes, you can compare two models and say that one has gotten better, but it's we're assessing effectively distribution, and usually we don't. In a practical application, our task isn't to predict distributions; it's to predict an output. On the other hand, we can do more task-specific evaluations, and we can, here the form is generally we're going to compare the model's most likely output or something like the most likely output to some kind of human-generated reference output using a task-specific evaluation metric. So these task-specific evaluation metrics are things that try and take a pair and they say, okay, this is what I expect, and this is what I've given, how much should I sort of penalize this? And this is defined by domain experts. They're usually pretty easy to implement. They're okay to interpret. There are certain challenges. Some tasks, there isn't a single right answer. And if you sort of force the user to have a single right answer or maybe a small set of right answers, this can be a bit difficult, but in some cases, it works. And then finally, we can say, human evaluation is a possibility. This is, of course, very hard to implement in that it's expensive and time consuming, but it's relatively easy to interpret. Although I think sometimes the value of human evaluation can be overstated. People may give, good, they understand the task, but they often are inconsistent. They get distracted and things like that. And so to control for this, you have to, basically do a lot of evaluation. So it can be rather tricky. So I'm going to generally evaluate on conditional language models. If you want to look at how well you're doing, try and find a good task-specific automatic evaluation. That's probably the way forward. So the general frame that we're going to be working with here are what are called encoder-decoder models. So what we're going to do is encode X into a fixed size vector and decode that into a sequence of words W. And there was a question earlier about kind of representing the past in terms of a fixed size vector and its limitations. And we're going to address that shortly, because I am going to argue that that is certainly a big problem. But this represents a very important way of thinking, and even in the relaxations of this, you can sort of see some of the more recent models as operating as encoder decoders. They just work with variable sized inputs. So the nice thing about this is we can model a lot of tasks in different ways. So for instance, here is a translation task. We have some encoder which takes input sequences X in some language, builds us a vector representation there in the middle, and then we're going to have a decoder which is going to spit out words one at a time, conditional on that input and the previous words. That will be a translation, and we'll learn the whole thing via backpropagation. If we use a different encoder architecture, we could imagine having a picture of an image coming in, some sort of representation, and then we generate an image caption. So when we're working with these, we have two questions. So first, how do we encode X into a fixed sized vector representation? And this is going to be problem or modality specific. And second, how do we decode that vector into a sequence of words W? And this next one is going to be less problem specific. So we can start imagining things like general purpose decoders. And we're going to describe a very simple solution using recurrent neural networks. So what is a vector representation of a sequence X? Well, we've just spent a long time answering this question. So a very good way is to say, let's read the sequence and take the final state. Maybe we'll take the average over things. We've got a bunch of options here. These are the kinds of experiments that you'll run for your problem to see what works, best. And now what we want to answer is the question of what is the probability of a sequence Y given X? And so this is a little bit different, but it's not going to turn out to be too different. So we're going to build our representation of the input using an RNN. And now we're going to sample from an RNN conditional on C. And the way we're going to do this is we are going to make the input representation, that H naught that we started with to kind of the base case in our inductive definition of RNNs, we're going to make that depend on the output of the first RNN. So we've got two RNNs, one that encodes and the other that decodes, starting from a representation of that was computed by the first one. And then everything works as promised. So this is quite a simple idea. It uses the pieces that we've seen before, and moreover, we know how to train this, right? We just backpropagate through, and rather than just backpropagating through to the representations of the words in the language modeling side of things, in the target language, we're also going to be backpropagating all the way through into the components of the RNN that are in charge of reading the input sentence and building a representation of that. And all of these things are going to be updated so that the translation quality becomes best. So you can also here start to see some of these questions about, if gradients flow and every step they take, they get smaller and smaller and smaller, you can see how the importance of not losing too much information or not making them too small is if you want these things to learn effectively. So we'll return to these models in a moment, but I want to talk briefly about algorithms for decoding. So we talked in the first part about sampling from these models, but sampling is a little bit funny. Every time you run it, you get a different answer. In general, you might think you want to find something like the most probable output given the input. which is this argmax over all sequences W of P of W. And we can rewrite this in terms of our chain rule decomposed thing in terms of the argmax over all sequences of W. And then the thing we're maxing over is the sum over all sequences in the current candidate translation, where we add the current probability to the prefix to the current word to the prefix and the conditioning context representation. So one of the things that's difficult here is that we can't actually solve this maximization problem. This is actually a very hard search problem, computationally hard. And so we often will approximate it with a greedy search. There actually are some ways to write this down so that you can solve it exactly, but it's extremely slow. And so we approximate it often with greedy search. What greedy means is we take a series of maximization decisions and we don't revise them. So we say, what is the very best thing that I could do in the first position? And then given that, what's the best thing I could do in the second position, and so on. And we repeat this process until we say the best thing we could do is end the sequence, or we say go too long, because sometimes these models, the best thing that they do is they just want to keep going. So you always have to worry about these corner cases. And I will leave it to you for a moment to contemplate why this is not going to give you the overall global maximum, but instead is only an approximation to this. So a slightly better approximation to finding the map solution, the maximum a posteriori solution, is to use what's called a beam search. And this might also give you a little bit of an insight into why it is that this greedy search isn't finding the best solution. Beam search is also not going to find the best solution, but it may find something a little bit closer. So let's imagine we are doing a translation problem. Here's our input, and we are going to do a beam search where we're going to keep track of top two hypotheses at each stage in the search. So we're going to start with an empty string, and we're going to have a score associated with this. So that's going to be log prob 0. That S symbol there, that means that's the starting symbol for. So that's going to be kind of what happens before the sequence starts. And then what we're going to do is at time step 1, we're going to get the two best predictions out of the model. And we're going to write down the log probability of the full sequence, which is just going to be the log probability of the previous state plus the log probability of the current thing. So here there will actually be many possibilities, and we're just going to keep the top two. Now for this top two, we're going to, again, find the best continuation of each of these things. And you're going to see very quickly that, just because we keep track of 2 at each step, as the sequence continues, this is going to grow exponentially, and we don't like that. So at the time step 2, what we're going to do is, after we've expanded all of the previous elements, we're now going to keep track of just the top 2 elements that are left there. And you'll see here I have kept 2 elements that are sort of in 2 different branches of this tree. That doesn't necessarily have to be the case. It may be that one of those previous branches dies off completely, and we consider only the prefix, maybe starting with I. And then we've gone down from 2 to 4. So we've clamped down on this growth. So rather than going from 2 to 4 to 8, we've gone from 2 to 4 and back to 2, and now we're going to go from 2 to 4 again and back to 2. And when we get to the end, then that's when all of the elements on the beam have reached the end of sentence symbol, or a maximum limit. We then select the one that has the highest log probability, and we follow these pointers back, and that recovers our translation. And I did make up these numbers here, but these are perfectly plausible numbers that could come out of a translation model. And you'll see that if we had greedily chosen things in this model, we would have found a different solution at the beginning. So we would have actually picked beer as the first word rather than I, which would have resulted in a different sequence. So this should give some intuition for how beam search can find different things. And in practice, for a lot of tasks, beam search is close to state of the art. It turns out that you don't actually want to find the global argmax. So the fact that we don't have algorithms that enable us to do that is good. This has to do with the fact that we are actually our models, as powerful and wonderful as they are, don't always estimate the very high probability elements in the distribution very well. And this greedy search or beam search provides a little bit of a bias that turns out to be quite useful for decoding. So this is one of the sort of serendipitous things where the algorithm that we sort of had to resort to as an approximation turned out to have a kind of regularizing effect. And I'd actually say this is not an accident. There are many things in the history of machine learning where we started with one optimizer and things seemed to work really well. And then when we improved the optimizer, things got worse because it turned out that kind of having a bad optimizer had a regularizing effect. So there's some famous stories back in the day when kind of logistic regression started being used for the first time in NLP, and they were working with very bad optimizers, and it worked great. And then when they fixed them, they immediately got overfitting problems. So there's something similar in decoding here. Okay, so are there sort of any questions I can answer right now about kind of the conditional language modeling setup at all? What are my views on non-autoregressive generation? Well, I work on non-autoregressive generation quite a bit. I think it is a very interesting thing because so when you generate things in different orders, you have different inductive biases. So when you think about this problem of passing information around the model, if you can co-locate the events that are kind of mutually influential, you have perhaps an easier time of learning things. And so I spent a lot of time pushing on that hypothesis. And I have to say, I have somewhat given up on that as being a sort of crucial way forward. Our models these days are incredibly good at elevating the kind of relevant information across even relatively long sequences just in standard autoregressive models. For speed reasons, there are some interesting possibilities here. If you are scoring whole translations or whole outputs in parallel, you can potentially decode more quickly. And so there are definitely interesting applications there. And I'm also concerned that these issues where when we find the global optimum with sequence models, we often find that these models are not particularly well calibrated. So I'm worried we're sort of painting ourselves into a corner where our models are poorly calibrated with respect to kind of where their mode is, the kind of maximum probability outputs. They tend to always have kind of degeneracies. And so we are also dependent on using these poorly understood decoding algorithms to make them work. And I feel like some of the non-autoregressive modeling opportunities that are out there could let us fix some of these issues in more robust ways, so that we no longer have to depend on broken algorithms in order to get good performance. And you might say, well, why do we worry about whether we are doing a sort of inexact search if it works well? Well, look, history is long and we're nowhere near solving all the problems we need to solve. And so I think we need to, we need to be careful not to depend on things where every step we take, we have to reevaluate all of the steps that we've built on top of, because there's, as things start to change and all of this is just sort of empirically contingent, we get a larger and larger design space, and every new change we make, we kind of have to retest the whole edifice. And so I'm worried about the sort of sustainability of models that are built on just kind of empirical accidents. Now, I may also be wrong here, and we turn out to have very good reasons that we can depend on for these models being stable as we build on top of them, even if they seem, even if we don't understand them all now. But I think that will also, we will understand that better by pushing them with alternative parameterizations like non-autoregressive models. Is there some way better than beam search recently for finding the global optimum? Well, you can run basically, when you're working with these probability models, we can estimate, we always know at every time step that the maximum log probability you're going to get is 0. In fact, we can do better than that, and we know the maximum probability at every time step. So what that means is that when we've got a high scoring element in the beam, and if everything else in the beam has a low scoring beam, has a lower score, there is no extension that you can make to any of those elements in the beam that will increase the score. So that allows you to prune things a little bit more aggressively. And so there are a couple of heuristic decoding algorithms that allow you to exploit that. But there are no guarantees. There is basically no way to know, or some model may have some sequence that these algorithms will fail to find a solution on. In practice, this doesn't seem to be the case, but there are no guarantees. How do we differentiate between LSTMs and bi-LSTMs of RNNs? So we'll talk about bidirectional LSTMs in just a moment here. So why don't we move on, and then we can return to these questions. Okay, so encoder decoder models like this compress a lot of information in a vector, and one of the problems is that gradients have a long way to travel, and even with the innovations that we talked about with LSTMs, they can forget. In fact, that architecture I showed where you read with an RNN was actually, when that was implemented, it was done with an LSTM, and then the decoder was also an LSTM. And when they did that work, they found that they worked on translation to do this, and they found that by reversing the input sentence, they got much better performance. And what happened was that meant that when you started generating the output sequence, you were very close in time to the beginning. The LSTM had just read the beginning of the input sequence. So the beginning of the input sequence was close to the beginning of the output sequence. And because the languages they were working on, things like French and English, tend to put words in similar orders, it meant that related events were very, very close to each other. And that turned out to help the model learn. So sort of it meant, in the sort of expectation, the difference between sort of the thing you conditioned on and the event that you predicted were kind of just as far apart in both cases. You still found that because there were a few cases where things were likely to be very close together, that sort of bootstrap learning. So these things are actually quite hard to reason about. But it showed that forgetting was a problem. So maybe we can avoid sort of both of these problems. So we're going to motivate what's called attention here to solve this. So what we're going to do is, rather than representing a source sentence, we're going to consider the problem of translation as our task here. But this generalizes to a whole bunch of other stuff. So we're going to represent the source sentence rather than with a vector, with a matrix. And that matrix is going to grow as the source sentence increases in size. And then we're going to generate a target sentence from that matrix. And these two steps are the algorithm for neural machine translation and how we introduce what's called attention, which is a very important technique in building neural networks in 2021. Okay, so what's the problem with the fixed size vector model in translation or images or anywhere? Well, sentences are of different sizes, maybe contain different amounts of information, but vectors are always just one size. And so our solution for this is we're going to use matrices instead. And we're going to construct them so that these matrices always have the same number of rows. So I call rows the last dimension. I'm sort of doing row major notation throughout this. But the number of columns is going to depend on the number of words. And in fact, we're going to say that the number of columns in this matrix representation of the input is going to be the length of the source sentence. So I'm going to call the source sentence F to convention in machine translation to have F and E as your two variables. And this goes back to the first papers on statistical machine translation, where they worked on French and English sentences. So basically, this is going to look like this, where we have different sentences, and they're going to be represented in different ways. And so our first question is going to be, well, how do we build these matrices? So the first thing we might do is we can represent a sentence by stacking vectors into a matrix representing the sentence. It's easy and fast, but it has the following limitations. There's no positional information about the words in the representation. And okay, well, you can say, well, we can add in some information for each position. That'll give us a little bit of information about position. And we'll return to this as a technique later on. But the more serious problem with this is that word meanings depend on the context that they are used in. And when you're doing translation, we don't translate word to word between languages. We translate between kind of the meanings of words. So we have to recover that context-dependent meaning if we want to have any hope of doing well at this task. And you can imagine similar analogs for any other kind of language generation task. If you are doing caption generation, understanding, say, all of the objects in the image are going to depend on kind of their relations to each other and things like this. Okay, so that's a bad idea for building the matrix, but simple. Here's how it looks schematically. So here's a very useful technique, and this is a general purpose technique also for kind of building good representations of sentences for many tasks. So we're again going to have one column per word, and we're going to have each column, so each representation of each word, and it's going to have two halves concatenated together. So the first is going to be what we might call a forward representation, which is going to be the representation of a word together with its left context, and a reverse representation, which is going to be the representation of a word and its right-hand context. And the way we're going to do this is using bidirectional RNNs. And I actually find the term bidirectional RNN to be a little bit misleading, because these are actually just two unidirectional RNNs, but they run in different directions, and then we stack them together. So when we, so we're basically going to read the sentence from left to right once, and then we're going to read it from right to left. And then for each position in the sentence where they correspond, we're going to stack those together as the representations. And then the left to right representation becomes that forward representation, and the right to left representation becomes the reverse representation. And you can see then that this is actually quite a nice representation for words in context, because at both times that HT in each of these models, obviously the most salient information at that point is going to be the XT that was just fed in. So the current word, which, yeah, if you want to build a representation of a word in context, you probably want the word to strongly determine its representation. But then there's also going to be information coming from all of the neighbors, all the way to the end of the sequence to the right through the reverse representation, and all the way back to the beginning of the sequence in the forward representation. And so by concatenating them together, we just let these two words get kind of all of this information present together with an emphasis on the current word. So it's really a sort of appealing representation to me. So basically, we're going to here run an RNN. We're going to keep these hidden representations, which I've annotated with a right arrow above them. We're going to do the same thing with the left going RNN, and we're going to then concatenate each of these things for every position, and this will look like this. And this is quite an effective representation for many things. Okay, so now we turn to the question of generating from matrices. I should say, actually, let me say before this, there are other ways we can generate these things. We'll turn to some of them, one more of them a little bit later on, but this is kind of a good starting point to see just how you might think about some of these things. So we have this matrix F representing the input, and we're gonna be able to know how many rows it has. So we're gonna know what it's, we're gonna know, its first or last dimension, depending on how you think about these things, and it's gonna have a variable number of columns. So now we need to generate from it. So we've seen, a bunch of work, or a bunch of slides showing how we can modulate the behavior of an RNN, for instance, via a vector, but we don't have a vector, we have a matrix. So we're going to turn to this idea due to Dmitry Badnow from 2015, who proposed using what's called attention for translating from matrix encoded sentences. And the high level idea is that we're still going to generate our output sentence word by word using an RNN or GRU or LSTM, any of these variants. And at every output position T, the RNN is going to receive two inputs in addition to its recurrent inputs. So a fixed sized embedding of the previously generated output symbol. So obviously at time step 2, when generating the output, we want to know what actually got generated at time step 1 so that we have a good continuation of that. So that's how that information is gonna be propagated forward. And then we're also going to build a fixed sized vector encoding a view of the input matrix. And we're going to view that input matrix in different ways as we progress through the sentence. And the idea is that if we learn a good way of viewing that input matrix that evolves over time as a function of the progress of that output RNN, we'll be able to grab the information that we need from that matrix as we generate the output. So Badnow proposed, and we have continued to do this as our definition of attention, but we're going to do a weighted sum of the columns of F. So remember, we have a variable number of columns, and if we assign a weight to each of them, we're going to end up with a fixed sized vector that's going to encode things. So if we have a vector AT, which is going to say how much to attend to each of these columns, that's just a matrix vector product FAT. And the weighting of the input columns at each time step AT is called attention. So what does this look like graphically? So if we recall our RNNs, we go through and we generate things one word at a time, starting from the start symbol. It continues. So at each time step, we're feeding in this embedding of the previously generated token. So now we're going to feed in a little bit of side information. So first, we're going to assume that we have built our matrix using whatever technique that we like, and we are going to construct using the previous hidden state a weighting of all of these columns. And what we're going to do is take the previous hidden state, in this case 0, and we're going to maybe do some similarity function of that 0 vector and all of the columns of this. And we're going to do the same function for each of the columns, and that's going to give us a score, and we're going to normalize that into something. We're going to pass it through a softmax, and that's basically going to give us a weighting that sums to 1 over all of the columns. And then we're going to add together those columns according to that attention vector at time step 1, and that's going to give us the second input. And that input, together with the embedding of the previous symbol, in this case the start symbol, we're going to feed into to the RNN cell. So basically there are 3 inputs here in a classical RNN. There's HT-1, there's the embedding of the previous output symbol, and then there's this current attention-dependent embedding. And then we're going to compute HT and then move on and generate our prediction. And here we'll sample. And now we repeat the process, and we keep doing this until we sample the stop symbol. And one of the really interesting things about this is at each time step, we can kind of visualize these attention vectors, and we can get some idea of where the model is looking. Now, the attention, there are obviously there's some uncertainty where you have optionality in translation. So you can often start the second half of the sentence, beginning of sentence, and so this isn't attention isn't really a kind of active thing. It just sort of says what are the inputs that are influencing the model, and sometimes they seem a little bit counterintuitive, but often you'll see some kind of sensible patterns where you kind of move in a diagonal through the sentence as you're generating translations. So how do we know what to attend to at each time step? That is, how do we compute AT? Well, what we need is a weight for every word. So this is basically going to be an F-length vector of A. So we need 1 score for every column in the input matrix. And so here's a simplified version of Badnau's solution. So we're going to use an RNN to predict the model output. So if we call its hidden states ST, ST is going to have a fixed dimensionality, which we'll call M. At time t, we're going to compute the expected input embedding, which will be just a linear transformation of that hidden state, of the previous hidden state. And V is going to be a learned parameter. And then we're going to take the dot product of this RT with every column in the source matrix to compute what you might call the attention energy. So these attention scores. And that's just this transpose of F times RT. And that you'll see has a dimensionality of a vector with the number of elements being equal to the number of columns in FT. So if we exponentiate normalize with the softmax function, we can say that is AT. So finally, the input source vector at time t, this current context vector CT is equal to F times AT. So this is basically using ST-1 to make a decision to construct what you might call a query to go into F and find little bits that are useful. And because V is there, it lets you have some parameters that figure out what are the useful things that you should be looking at in S to make a good decision about what things to attend to next. And all of this stuff is learned via backpropagation. All of these are differentiable functions. Okay. So attention is closely related to pooling operations in ComNets and other architectures. What's interesting about this attention model is it only seems to really care about content. There's no bias in favor of diagonals or short jumps or fertility. There's been some interesting work that's attempted to add other structural biases, but there's still a lot of opportunity there. It's similar to alignment problems that come up in things like stochastic machine translation and other problems, but there are important differences. So one is that alignment makes stochastic but hard decisions. Even if the alignment probability distribution is flat, the model picks a single word or phrase, and if you pick something else, the model behaves differently. Whereas attention is soft, where you just add all of the words together. And so if you have flat attention, you're kind of looking at everything, and if you have very peaked attention, you're kind of ignoring a lot of stuff, and the behavior is going to be quite different. But every time you run the model, you'll be attending to the same things until you change the inputs to the model. So the predictions, for instance, that are sampled. Okay, so I would say attention, I wanted to introduce it this way because these are, first of all, still quite important models. Attention is used in a variety of contexts, but this let us sort of isolate attention in just one way. But now I would say most sequence modeling is carried out using an architecture called transformers, where we represent words in context and sequences using attention only. So we get rid of these kind of recurrent connections and just use this attention mechanism at every time step to go out into the context and attend to everything that we need in order to build a good representation at the current time step. And this is going to simplify even more some of the memory problems. So, LSTMs, despite their sort of good ability to do error propagation and learning, they still require putting everything into this little vector that you have to remember about the past. And then if you combine that with attention, you can kind of go out and just grab what you need. And so the idea is to just every time you want to build a representation, for the, when you build the representation, just go into remember the context exactly and go and grab it when you need it. And that's what we're going to call self-attention. So the second thing that this is going to allow us to do is, because each kind of representation is going to go out and get what it needs, we're going to be able to compute the representation of every time step in parallel, provided obviously we've got all of the inputs at the same time. And because they are not going to depend recursively on everything else. And so if you do these two things, we call this architecture a transformer. Okay, so I'm going to motivate this with the task of Chinese English translation, and show kind of why we probably want to to build a good representation of words to do Chinese English translation. we might want to be able to go out and grab information from other parts of the sentence. So here is a gloss of a English opinion rendering of a Chinese sentence for those of you who don't read Chinese. And here are some of the possible ways you might translate each of the words in this sentence. And so some path you might think through this set of words will be a good translation. So basically, it'll be something like, yesterday I watched three movies. I watched 3 movies yesterday. Okay, so one thing to notice at the beginning, we have this character, and that could be translated either as I or me. Whereas in Chinese, you just have one character that means both those things. So, linguistically, we'll say Chinese pronouns don't indicate whether they're subjects or objects. But in English, we need to know this. So if we've been trained to build a representation of that first position to make English translation easier, basically, we want this guy to go out and grab information that will tell it whether it's a subject or an object. Well, we might notice that it is to the right of this somewhere is a verb. And so perhaps that's indicative of there being that this is acting like a subject. So we want to go and grab information about there being a verb to the next by perhaps attending to that verb. So we're going to go grab that kind of information. Another thing that is different in Chinese that we'll probably want to mark up the representations with if we want to facilitate English translation is Chinese nouns don't distinguish whether they're singular or plural, but in English we just have to do this. So this last symbol can mean movie or movies. Well, can we go out into the context and find information about whether this is singular and plural? Well, yes, we probably can. So it comes after the word 3, which probably means that it's plural. So we would like this representation to be a combination of movie and the fact that it's just after the word 3. Okay, so now let's look at this verb here in the middle. So English splits, we have the word verb watch, and we have the verb look, and we have the verb read, and these are used with slightly different, objects. So we watch a movie, but we read a book and things like that. Whereas in Chinese, you get to, use one verb, I guess, for these sorts of things. So maybe we need to go out and grab information about what the object of this verb is. So it seems like attention could help us with this. And then finally, you'll notice that Chinese verbs also don't inflect for tense. So they don't distinguish whether something is happening currently or happened in the past. But that's not to say that Chinese doesn't, communicate about the differences between the past and the present. Obviously, it does, just like everyone else. But in fact, this information just lives somewhere else in the context. And so we go out and we update the representation of watched with information about the fact that it comes after this adverb indicating that it happened yesterday. And so you'll notice that, in fact, not only have we gone out and gotten information from the context for this verb, we've gotten different kinds of information from different elements of the context when we've put this together. So you're starting to maybe see that not only do we want to go out and attend to other things in the context, but we want to attend to different kinds of things, and we want each word to be able to attend potentially to different kinds of things in different places. So let's summarize this. So different words need to obtain different kinds of information from different places. Words need to integrate multiple kinds of information. And although we didn't consider an example here, words may need to pass information along multiple hops. So let's design a model that supports all of these desiderata. So we're going to start with a matrix X representing our input, which is going to be with n rows and d columns, which is going to be obtained by stacking, n columns, d rows, which is going to be obtained by stacking word vectors together. So we're going to have one column for each element in the sentence. And we're going to transform this into a representation that integrates all of the necessary contextual information that's useful for the task. And so what's in this arrow? We're going to build this up. So the first thing that I sort of mentioned, if we stack elements, word embeddings that are independent together, is there were two problems. One, they don't know the contextual information. Two, they don't know where they are in the sentence. So the only thing they have to go on is their identity, and you can have the same word that occurs multiple places in the sentence. So we're going to need to do better than that. And so what we're going to do is concatenate with every position in the vector a little bit of what's called positional information. And you could imagine learning this. So for like position 1, we're going to have an embedding. Position 2, we're going to have a different embedding. But in practice, we often will just create a set of dimensions that have sinusoidal components. And these will give you a sort of soft binary counter that with things moving at different frequencies. And as you, and basically this will let words that are close to each other, they'll be similar in their inner product space. And different dimensions will let them attend sort of closer or further away from each other. So this is a little snippet of what some of these dimensions look like. You can see the formula that was proposed. Weirdly, this actually doesn't work really any better in general to learn these things. So this is a pretty good representation. Okay, so basically our X is going to be obtained by stacking word vectors and concatenating positional information. Okay, so now let's consider just one position. So say that verb that we want to go out and we want to attend, potentially grab information from around it. So it must decide where else in the sentence to attend to. We're also going to allow it to attend to itself, because maybe sometimes there's just no relevant information anywhere in the context. It's just going to say, you know what, I know everything I need to know, so don't bother grabbing information. So one way we might proceed is by taking, say, this xi, this x3 here, and we might compute the inner product of that with every column in the matrix. And so we can write this just as this X, big X, the matrix times the matrix that we're going to do. And this is going to give us a score for every position. That'll just be the inner product with every position. And we can normalize this into an attention rating. Now this is reasonable, but first I'll notice that we can do this actually in parallel for all positions by doing X times X transpose, and then doing softmax over all of the over the last dimension. And then we can multiply, we can go and get this attention by multiplying A by X, and this will go and grab all of the information from everywhere else and build a new matrix that represents the transformation of all of this stuff. Now, is the inner product a good attention matrix or not? Well, I'm going to say no. So the big problem is that each word is always going to want to attend to itself. So the first problem is that an inner product is going to be maximized with the same kind of vector, assuming these things are all normalized to the same. We can assume for the purposes of this exposition that all of the vectors have length 1. And so the maximum is just going to be when the vector is itself. And we probably don't always want to just get information from ourselves, or preferentially. And the potentially more serious issue is that attention is symmetric. So just because the verb cares about getting information from that, say, yesterday word, that it is in the past tense, it doesn't necessarily mean that the yesterday word wants to go and get a bunch of information from the verb. So we don't want symmetry, and we also don't want sort of too much attention to the kind of current position. So let's revise. We need some parameters. So let's add a parameter w, which will be in d by d. And now we can compute x times w times xi. So we've put this kind of metric matrix here in between, and so we can call this a parameterized inner product. And this is going to let us control where we look. Attention is no longer going to necessarily be symmetric. It can be if that matrix has certain properties. And moreover, we can still do things very, very efficiently as sort of just a single operation where we multiply matrix X by matrix W by the transpose of matrix X. Okay, and then to attend to different kinds of attention, we can just add multiple W's. So we just do this process many times. Or equivalently, we can redefine W to be a higher order matrix, so a tensor of order 3, where we have basically we decide how many different kinds of information we want the model to go out and be able to get. We're going to call, or the transformer paper calls this attention heads. We'll call this H of them. And so often, you'll have something like 8 or 12, and we can use batched matrix multiplies to do this very efficiently. Okay, so what's the problem with H by D by D? So in general, in transformers, our models are big. We have maybe 1,000-dimensional word embeddings. Our X's are big. We've added some positional embeddings. All of this stuff is really quite large. So, if we have 1,000 by 1,000, that's already getting up to 1 million parameters just for this. And there are going to be other parameters coming. And now if we have multiple heads, that's many millions. This is going to be hard. And this is just deciding where to attend to. It's not doing anything with it. This is slow, and it makes learning hard. And you have to buy fancy hardware. So what can we do about this? Let's take another attempt. Let's use a low rank approximation of W. So we'll define 2 matrices, L and R, where L is in D by L and R is in L by D. And then we can think of W as being decomposed into the product LR, which is going to give us a D by D matrix. But we can then do our softmax, or we can compute our attention with XLR X transpose. And now we can compute the number of parameters in the model by setting L to be as small as we like. And in practice, we usually say that L is going to be equal to D by H, by the number of heads. So this is quite conventional. It works quite well. And then the output here is just going to be our softmax of XLR X transpose times X. Okay, so, but that only really goes through with if L and R are kind of single matrices. So how do we deal with this like multiple heads? So in practice, as I said, we'd like each of these heads to extract different information from different places. So we need to transform X, where we want also the result of this to be we want x to be transformed before we attend to it. So we want x to be multiplied by p, and we're also going to want p to be low rank. So we're going to basically project p. We're going to project the value of x down to something rather small. So again, this let's call it L again. And in the case of multiple heads, we're going to basically be picking different bits of information out of every column of X and projecting that information from the full dimensional D size down to the smaller dimensional L. So basically what this is saying is like, okay, over here, maybe I'll go and get information about number. Over here, I'll go and get information about tense. And I don't have to sort of get all the information about that word. I'm going to just go and pick out the little bits that I want. And this P, this projection matrix is making this stuff available. Okay, so now putting this together, so now we have three auxiliary parameters. We have L, R, and P. We're going to compute a softmax of X, L, R, X transpose. And then for each of those heads, we're going to aggregate information from XP. We'll call this Z. And now what we have is basically a matrix per head, which is going to be in this sort of small, we're going to have one column per word position, and it's going to be in this sort of small L dimensional space. And so we have one of these matrices per head. But now we'd like to get back to our kind of matrix representation. So what we're going to do is we're just going to stack these heads on top of each other and concatenate these vectors. So head one will be sort of in the first L positions, head two will be in the next L positions, but they're going to have the same number of columns, so it all works out. This will be basically the reshaped matrix then after the concatenation is going to be, it's going to have n columns by L times H rows. And this is why when we divide D by H to get our L, then we end up having a N by D matrix again after this process. We conventionally, run one more linear projection at this point. So there are sort of two purposes for this. So if L times H doesn't have D, if we used a different number of dimensions, we want the output to have the same dimension as the input, because we're going to stack these things in a moment. We are also going to want to mix the information together. So right now, these things live in different parts of the matrix, in different parts of these vectors. And we want all of these things to be able to mix together throughout the vector so that the information can be conjoined. So we're going to do a projection by a final matrix O. And this is going to be down here at the bottom, the final computation that we do in order to get the self-attention representation of words. And by adjusting the number of parameters, the H's, we will end up with, we can control sort of how much capacity the attention model has and how much information can be grabbed together from different parts of the sentence. Okay, so why do we like these? Well, these operations are very efficient. They can exploit batch matrix multiply operations, so they're very fast on GPUs and TPUs if you use those. In practice, we implement these things using the einsum operation, which most frameworks like NumPy and Torch and JAX and all of these things have available. I would encourage you, if you go out to implement these things, to look at this. And these are extremely fast in modern accelerators. And there's the fact that we can do effectively kind of one operation to build a representation of the input is a huge advance over what the state we faced with LSTMs, where we could only compute HT after we'd computed HT minus 1, and HT minus 1 depended on HT minus 2, and that was a very sad state of affairs if we wanted to train these things quickly. Okay, but we're not done yet. So transformers actually consist of two parts. So we are going to stack these things, but before we stack these things, we're going to have a second half of this layer. So first, we're going to do the self-attention process where we go out and grab information. And now we're going to take the result, what we're calling Y here, and we're going to further transform it by passing each position through an MLP. And this is, MLPs, as we said, allow us to learn nonlinear functions of the input. So far, there's a little bit of a nonlinearity in the Softmax, but basically we only have a linear model so far. And so we need this MLP in order to realize the full power of full representational capacity of deep networks. And so what we're going to do is say that our final output F is going to be this matrix Y times W plus B. So Y is going to project or W is going to project this Y matrix that we've ended up with into the hidden space. We're going to add a bias vector to all of the columns. We're then going to pass that through a ReLU. So this is another nonlinearity that works quite well. And multiply this then by a matrix V, and then we can at a bias. We actually are not, we don't generally explicitly write it this way. I'll talk about this in a second. And in practice, this W matrix, so remember we've just projected this back. So we've got F as a D-dimensional N by D structure. And what we're going to generally do is increase the size increase these columns. So we want them to be bigger. So we want K to be large in some way. And in fact, I'd say these days, the kind of larger you can make the feed forward layers, the kind of better the performance gets in a lot of cases. But there are a huge number of parameters in this part of the model, and it's very much sort of a question of how much memory can you afford. But people are working with sort of ever increasingly large W sizes. But often a reasonable starting point is something like D by 4. Okay. So one other thing that we're going to do here is we are going to be stacking these things. And our assumption is that when we do attention, we're going to go out and grab information. We're going to grab a little bit of additional information. But really, what we want is the information that we already had in each position to kind of carry forward. And we want gradients to be able to flow to low parts of the model from like higher up relatively directly. So we're going to compute, actually Y is going to be this attention process, but we're also going to add in the X, which is the same shape. We've guaranteed it's the same shape as the result of this attention process, so that so gradients can flow directly down. We're going to do the same thing with the feed forward layer. So we're going to have this complicated, or this, this 2-layer neural network here, but then we're also going to be adding in the result of the attention process Y, which also includes the direct path back to X. So you can sort of see that there are these additions that are kind of allowing gradients to kind of, yes, they can go through these attention and feed forward layer processes, but they can also just kind of go straight back down through to the inputs. Okay, so these final details. So these are the residual connections. They're going to make the models deeper and make deeper networks easier to learn. And then the second thing I will say, which I didn't show in the figures here, is that layer normalization is used, and this is going to rescale the columns of Y and F. So effectively, you can think about this as you subtract out the mean so that the mean becomes 0, and then you're going to divide by the standard deviation so that the standard deviation of all of the columns goes to 1. There are actually extra parameters, so you set the mean and standard deviations to a learned value, but basically what this helps do is prevents these values from sort of going to become too big or too small, and it's quite important. So to enable propagation of information over multiple hops and to learn more complex interactions, we're going to stack many of these layers on top of each other. So if you're working on, say, machine translation, it's quite conventional to use something like 6 layers or so of this to represent the input, but people are working with much deeper networks, 12, 18, 36. It's people are getting trying to make these things very big. Okay, so now we've built an encoder that uses attention to compute representations of words in context. And we could replace the bidirectional encoder used in the previous section of this. But we're going to now, here at the end, turn to how to build a decoder out of transformer components. So the transformer encoder that we talked about can attend forwards and backwards. And this is what makes them so powerful. But a language model can't look into the future for words that haven't been generated. I mean, at training time, it kind of could, but it wouldn't help you at test time because you wouldn't have predicted the words yet. And so we're going to introduce a very simple trick here that's going to manipulate the attention at every position so the word can only look to its left. And this is just an incredibly simple tweak to the model. So right before we do that softmax, we've computed this this matrix of scores where we have a score for every word attending to every other position, so an n by n score. And we're just going to add, this matrix M, which is going to consist of zeros and minus infinities, such that the pre-softmax attention scores are set to minus infinity for all attention from position I to J, where J is greater than I. So we're just not going to let a position attend to anything after itself. And then obviously when we pass this through the softmax, we're going to get zeros there. And so you'll always only be attending to yourself or to previous positions. And that is going to solve things. So the nice thing about this is at training time, we can still attend we can still compute the representations in the decoder for all positions in parallel. We're just preventing the model from seeing anything that it shouldn't by limiting the attention in this way. Okay, so the way we use this to build a language model, we actually don't need an encoder at all. We can just use this decoder that we've talked about. So we can say that we've got this matrix Y to the left, which is one that has this mask in it. And what we're going to do is build a sequence of transformations from our input X up to a final representation where we have one representation in each position. We're going to project that out onto our vocabulary, do a softmax, and that's going to give us a probability distribution over all words at that position, conditional on everything that happened in the past, which we see in the training data. And this is actually the basis for these large language models. So the example I gave at the very beginning of things like OpenAI's GPT-2 and GPT-3, the code generation thing, all they're building is just big unconditional language models where at training time, they're presented down at the bottom with samples of text they mined off the internet, samples of code they mined off GitHub, and then they're training very deep layers of these unconditional models using exactly this architecture effectively. Now, if we want to condition on side information. So when we're decoding, we want to look at that encoded information. We're going to incorporate conditioning context by attending into the source context C. So that's going to be represented as a matrix C. We're still going to have our L's and R's, and we are going to be able to compute our representation, though, on the basis of the thing that we're generating, our matrix Y. And we are going, though, to grab information from the source. But in addition, we're also going to be doing self-attention on the prefix of the things that we are generating. So we're doing two things. We're building a representation of the target history, and then we're incorporating conditioning context by attending into the source sentence C. Okay, so transformer summary. This is the current state of the art. It's a good mix of computationally efficient and reasonably effective model. It's particularly efficient because it can exploit the parallelism that current models have. So we can use the fact that we have these very, very wide vectors of processors that can do a bunch of computation in parallel. We don't have to run things serially. There's still many opportunities to improve things. So low rank approximations are one way to reduce parameters, and we do depend on them, but we might be able to get more effective reduction. So we are working with bigger models, but we still can't, it's a very inefficient way if we were to put back, instead of that LR factorization, if we were to put full W in there, that wouldn't be a sort of good addition of parameters. So although we want to increase the number of parameters we have to be careful about where we put them. One way of sort of improving parameter efficiency is maybe giving us better approximation. So another question, which is kind of interestingly open, is whether every attention head has to sum to 1. So maybe sometimes certain heads could be turned off. Another big question is whether attention needs to be denser. If we made it sparser, maybe we would learn it would be a better bias. We could certainly reduce computation if we didn't have to go out and attend to absolutely everything. And there's just a lot to think about here. So this is it. I know we're a little bit longer than we wanted to be, but I will take questions now here at the end.
Chris, thank you for the wonderful talk. We have 3 questions in the Q&A. Well, if some other questions arise in the meanwhile, I would propose that we could copy this to Slack, and then maybe later you could go there and answer some of them, okay?
Yep.
Okay.
What are the differences between the roles of self-attention and those of encoder-decoder attention? So self-attention is seeking to summarize either the history or the history and future of a word in context. Whereas attention in encoder-decoder attention is seeking to, given a current representation of a state, it's saying, go out and find the information in the context that's relevant. So if we go back and look here, I know I was a bit quick in this section. The lower expression here, which depends on X, is the target prefix, and it's basically saying, build me a representation for every word in its language modeling context in that first step. And then the second step says, go out, and this is the cross attention, which looks very similar to encoder decoder attention. It says C is my source representation. Go out and grab me information that looks like the thing that I have currently built as my representation of the target language prefix. So it does that in two steps. First, it takes this kind of parameterized inner product with all of the positions in the source sentence. That's this, the inside of that softmax. And then it multiplies the result of that softmax with each of the columns in that context matrix C to go and grab that information, and then projects that out and does some final transformations. And then it adds this to this representation that was computed as using the prefix attention. So I'd say self-attention replaces effectively the recurrent network kind of recursive decomposition of the history building operation in RNNs, and attention is cross attention is doing the same thing. Okay, can you link the parameters that you've talked about in the keys and values that are generally, oh, yes, sorry, I have a slightly idiosyncratic presentation here. Where's a good place to talk about this? Here. Okay, so if we look here, we've got A equals softmax XL RXT. XL is transforming every column in X into a series of queries. So every position will have a query, and R is transforming, RXT is transforming every column, but transposed into a row, into a series of keys. So we're basically saying what we're going to do with that product then is compare all the keys to all the queries. So XL builds the queries and RX builds the keys. And actually, I'm not distinguishing between, it's completely symmetric, like which is the keys and which is the queries. There is no real distinction, just and that's why I presented it a little bit in this way, because queries and keys are, it's a very evocative image in the paper, but there's complete symmetry. There's no difference between a query and a key, really. I thought this presentation of the mathematics would make it a little bit more clear, well, I hope, with what was going on. Okay, P and O don't seem to be mandatory. The reason we have LR is because we want the attention to be non-symmetric. So you're right, P and O are not necessary. The model will work happily just as well without them all. I mean, assuming you haven't changed, assuming you used L equals D divided by H. I do think you're likely to get into some trouble if you don't give the model a little bit more opportunity to mix things. I think learning you would basically need fatter feed-forward layers or deeper models if you got rid of the P's and O's. But I cannot say for sure whether that's the case. There definitely are transformer people who have run zillions of variants of moving parameters around, and it's an interesting possibility. Okay, Loic, can you please give us more insight into why residual connections make deeper nets easier to train? Yeah. Again, it's exactly this Jacobian issue where addition means that errors, that gradients have a path that propagate down directly to lower layers. So that's kind of the most important issue. The second is, I would say, there's a kind of inductive bias there that if you don't have a residual connection, you have to recover. The default is not, say, an identity function. So when you, say, pass something through an MLP. So in the transformer, for instance, after the self-attention process, yes, you can imagine sort of propagating information about the current word forward beyond self-attention just by attending fully to yourself. That's reasonable. But at that point, you pass it through a feed-forward network. If you don't have that residual connection there, that feed-forward network, to even just propagate information forward, it first has to learn the identity function, and then it has to learn to transform it. And so if you want to kind of get information from the bottom of the network to the top of the network by starting with things that are making sort of small incremental changes, the output of an sort of randomly initialized MLP is basically something like a zero vector. And so if that zero vector is used to modulate the input by small residual differences, information flows through much more easily. But if it has to kind of learn first to propagate information, the learning problem is very, very difficult.
Okay, Chris, thank you very much for this wonderful talk. I believe that you have answered all the questions, which is a record. Definitely. Okay. And okay, thank you again.
If there's questions, I'll pay attention to the Slack for a little while, and we can go from there. And I hope to see you all next year in person.
Yeah, in person. Yeah. Okay. Thank you very much again. See you.
Bye bye.
Bye bye.